Hello there, and welcome to Physics with William, where we take familiar parts of the world, look at them a little more closely than anyone reasonably needs to before bedtime, and discover that even the most ordinary things become surprisingly strange once physics gets involved. Tonight we are turning our attention to something that has probably been surrounding you since the moment you pressed play. Sound is so common that most of the time we barely notice it. A voice from another room, traffic somewhere outside, the quiet hum of a refrigerator, the movement of fabric against a pillow, the distant closing of a door, the soft rush of air through a vent, or perhaps nothing obvious at all except the faint sounds that appear once everything else has become quiet. We live inside a constantly changing environment of vibrations, and our brains are so good at interpreting them that we usually skip over the physics completely. We hear a voice and think of the person speaking. We hear music and think of the melody. We hear a floorboard creak late at night and immediately think of every possible explanation except the movement of pressure through matter. That makes sound a particularly good subject for a quiet investigation because it feels simple until we ask the most basic possible question. What is it actually made of? If you hold a stone, you can say that the stone is made from atoms. If you drink a glass of water, you can describe the water in terms of molecules. If you look at the air around you, even though you cannot see it, you can still say that it contains enormous numbers of molecules moving and colliding. But sound is different. You cannot hold a piece of sound in your hand. You cannot leave some sound sitting on a table and return to it later. You cannot open a cupboard and discover that someone forgot to put the sound away. Sound exists while something is happening. A guitar string moves, a speaker changes position, air is compressed and released, molecules move back and forth, a disturbance travels through a material, and eventually some part of that disturbance may reach your ears. At the level of everyday physics, this gives us an answer that seems perfectly satisfactory. Sound is a mechanical wave. Something vibrates. That vibration disturbs nearby matter, and the disturbance moves through the material. If the sound is travelling through air, the air molecules do not race from the source all the way to your ear. They mostly move back and forth over tiny distances while passing the disturbance along. The pattern travels much farther than the individual particles carrying it. You can imagine people standing close together in a long line. If the first person gently nudges the second nudges the third, and the third nudges the fourth, the disturbance can move down the line even though nobody has walked very far. Real sound in air is more complicated than a line of people politely nudging one another, but the basic idea is useful. Matter responds locally, and the effect spreads. That description explains a great deal, but it leaves another question waiting underneath it. Matter itself is quantum mechanical. The molecules in the air are quantum objects. The atoms in a metal bar are quantum objects. The particles that make up those atoms obey quantum physics. So if sound is a pattern of motion in matter, and the matter itself has a quantum description, then sound must eventually have one too. The closer we look, the less comfortable the ordinary picture becomes. A smooth wave begins to reveal a deeper description in which energy does not always behave as though it can be divided into endlessly smaller amounts. Instead, certain vibrations can be described in discrete quantum excitations. Physicists call these excitations phonons. That word will become important later, but it is worth being careful with it from the beginning. A phonon is sometimes described as a particle of sound, and that phrase is useful as long as we do not imagine the wrong kind of particle. A phonon is not a microscopic pellet of noise flying through the room. It is not a tiny object with a little destination marked on it, leaving a loudspeaker and heading directly toward your left ear. It is a quantum description of collective vibration in matter. The collective part matters. A sound wave is produced because many pieces of a material move in a coordinated way. When quantum physics describes those coordinated vibrations in certain systems, the excitations can behave mathematically and physically enough like particles that treating them as particle-like objects becomes extremely useful. Before we go any further, notice what you can hear where you are right now. You do not need to concentrate very hard. In fact, there is no need to make this into an exercise. Just notice whether your surroundings are completely quiet, or whether there is a background sound that your attention had filtered out until now. Perhaps there is rain. Perhaps there is a fan. Maybe you can hear distant traffic, a television somewhere else in the building, the heating system, a computer, a pet moving around, someone talking outside, or your own breathing. If you are listening through headphones, you're also hearing a device perform a surprisingly complicated physical task very close to your ears. A tiny moving component is creating variations in pressure. Those variations are travelling through the air in and around your ear. Your eardrum is responding. Small bones are transferring motion deeper into the ear. Fluid is moving. Sensory cells are responding. Electrical signals are being produced, and your brain is turning all of that activity into the experience of a voice. You may be listening from a bedroom, a sofa, a train, a hotel, a quiet office, or somewhere completely different. So I would love to know where in the world you're listening from tonight, and what sounds are around you while you listen. It is an unusually fitting question for this subject, because every answer describes a slightly different physical environment. One person may be hearing heavy rain against glass, while another hears insects outside an open window. Someone may have the steady background noise of a city, while someone else may be in a place quiet enough to notice the building itself shifting as it cools. We usually talk about locations by describing what we see, but sound gives every place its own physical character as well. If you enjoy these slower explorations of physics, and you find them useful for relaxing while still giving your mind something interesting to follow, you can like the video and subscribe to Physics with William. It helps more curious listeners find this quiet corner of science, including those who have somehow reached the end of a long day and decided that the appropriate way to fall asleep is to investigate the quantum nature of vibration. There are worse choices. At least this one is unlikely to require getting out of bed. The strange thing about sound is that it sits directly between two ways of describing nature. On one side is the world we experience every day. In that world, sound behaves like a continuous wave. We can record it. We can see its shape displayed by audio equipment. We can make it louder or quieter. We can combine different tones. We can send it through walls, pipes, water, wood, and metal. Engineers can predict how rooms will echo. Musicians can control frequencies and harmonics. Doctors can use sound at frequencies beyond human hearing to produce images of structures inside the body. All of this works extremely well without asking what an individual quantum of vibration is doing. On the other side is the microscopic world. Atoms in a solid are not simply motionless dots fixed permanently in place. They vibrate. They interact with neighbouring atoms. They exchange energy. The organised motions of enormous groups of atoms can be studied as collective patterns. Quantum mechanics changes what values of energy are allowed for those patterns, and that is where the idea of the phonon becomes useful. The smooth vibration we describe classically can, under the right conditions, be understood as containing quantum excitations. There is a useful comparison with light, although we should not push it too far. Light can often be described as a wave. It produces interference and diffraction, and in many ordinary situations the wave description is exactly what we want. Quantum physics also tells us that electromagnetic radiation can be described in terms of photons. A bright light contains an enormous number of photons, so the individual quantum behaviour usually disappears into the overall result. Sound has something loosely similar. A large-scale sound wave can be described as a smooth classical disturbance, while the microscopic quantum description can involve phonons. But photons and phonons are not the same type of thing. A photon is associated with the electromagnetic field and can travel through empty space. A phonon depends on a material system whose collective vibration it describes. That difference explains one of the familiar facts about sound. Ordinary sound cannot cross a perfect vacuum because there is no material there to carry the mechanical disturbance. Movies have trained us to expect large explosions in space to arrive with an impressive noise. Because an entirely silent explosion would feel disappointing, after someone has spent a large portion of the production budget making it look dramatic. Physics is less concerned with dramatic timing. If you were separated from an explosion by vacuum, there would be no ordinary sound wave travelling through that empty region to your ear. Light from the explosion could reach you because electromagnetic radiation can propagate through vacuum, but sound needs matter. Inside matter, however, there is plenty happening. Imagine a long solid object. Its atoms are connected through electromagnetic interactions. Push on one end and the atoms near that end move slightly from their usual positions. Their movement affects neighbouring atoms. Those atoms affect others, and a disturbance can pass through the material. Different materials respond differently because their microscopic structures and interactions are different. This is one reason sound does not travel at the same speed everywhere. Air, water, wood, glass and steel do not provide identical environments for a mechanical wave. Our ears normally hide all of this from us. They do not present a scientific report describing molecular displacement, pressure variation, energy transfer and frequency. They give us experiences. A low note feels different from a high note. A whisper feels different from a shout. A familiar voice is recognized almost immediately. We can tell whether a sound appears to come from the left or the right. We can notice reverberation and distance. We can sometimes identify a room without seeing it simply from the way sound behaves inside it. Your auditory system takes complicated physical information and turns it into something direct and useful. That can create the impression that sound itself is something separate from matter, almost as though a song is an invisible substance floating through the room. But the song you hear is a pattern encoded in physical changes. When recorded music is stored digitally, it is represented as information. When the music is played through a speaker, electrical activity causes a physical component to move. That movement creates changes in the surrounding air. The pressure variations travel toward you. Your ear responds to them. The pattern survives through several very different physical processes, which is why the same piece of music can begin as data in a memory device and end as the movement of structures inside your ear. The quantum description does not replace that story. It adds another level underneath it. This is an important point because quantum physics is sometimes presented as though it announces that everything we thought we knew was wrong. Usually the relationship is more practical than that. Classical physics works extremely well within the conditions where we use it. If you want to design a concert hall, you do not normally begin by counting phonons. If you want to understand why your neighbour's music is coming through the wall, the classical behaviour of sound waves will probably explain the problem without requiring an advanced discussion of quantum excitations. Quantum physics becomes essential when the scale, energy, temperature, or sensitivity of an experiment makes the discrete nature of the system important. This happens in some remarkable modern experiments. Researchers can create very small mechanical systems where individual vibrational excitations matter. They can cool devices until thermal motion becomes extremely weak. They can couple mechanical vibrations to electrical circuits or light. They can study the exchange of individual quanta of vibrational energy. Under those conditions, the idea that sound is simply a smooth wave is no longer the entire story. The quantum nature of vibration becomes something that can influence measurements directly. Even then, the word sound needs a little care. Human hearing covers only a limited range of vibration frequencies. Physics is not restricted by what our ears happen to detect. A material can support vibrations far above the frequencies we can hear. Those vibrations can still be treated with the same quantum ideas. Phonons, therefore, are not simply units of audible sound. They describe quantized vibrational excitations in material systems more generally. Some are associated with vibrations that correspond closely to the sound waves we know. Others belong to modes of motion that no human ear could ever hear directly. There is something reassuringly ordinary about the origin of all this. We are not beginning with an exotic object found only inside a distant star or an experiment that requires a machine the size of a city. We are beginning with vibration. A ruler hanging over the edge of a desk can vibrate. A guitar string vibrates, a loudspeaker vibrates, your vocal cords vibrate, a glass can vibrate, a building can vibrate, the ground can vibrate, a crystal lattice can vibrate. Once matter can move and interact with neighbouring matter, waves become possible. The quantum step appears when we ask how those vibrations behave at the microscopic level and how their energy is organised. In classical physics, we can imagine reducing the energy of a vibration smoothly. Make the motion smaller, then smaller again, then smaller again. Quantum mechanics tells us that when we describe certain vibrational modes, their energy changes in discrete amounts. One excitation can be added, another can be removed. The language begins to sound particle-like because the mathematics and experiments allow us to talk about these individual units as identifiable excitations. This does not mean that a loud sound is just a bucket filled with tiny audible beads. The relationship between the classical wave and the quantum description is subtler. Large numbers of quantum excitations can combine in states whose behaviour closely resembles the smooth waves of classical physics. At the scale of everyday sound, the number of relevant microscopic excitations can be so enormous that treating the vibration as continuous is not merely convenient but extremely accurate. The quantum details are still underneath, but they do not announce themselves every time someone closes a door. That is a pattern found throughout nature. A gas has pressure even though no individual molecule possesses the pressure of the entire gas. Temperature describes the collective behaviour of huge numbers of particles. A wave on the surface of water has a clear shape, even though the individual water molecules are moving in complicated ways. Many useful features of the world appear when large numbers of smaller components act together. Sound belongs naturally to that family of collective behaviour. This is also why phonons are often described as quasi-particles. The name does not mean they are imaginary. It means they are not fundamental particles existing independently in empty space. They arise from the organised behaviour of a larger physical system. An electron can exist without a crystal surrounding it. A phonon, by definition, belongs to the vibrational state of some medium. Remove the medium, and you remove the physical system whose collective excitation the phonon describes. Quasi-particles are common in condensed matter physics, because complicated materials become much easier to understand when certain collective behaviours can be treated as if they were particles. Instead of tracking every atom and every interaction separately, physicists can describe the important excitations. Those excitations can move through the material, exchange energy, scatter, appear, disappear, and interact with other excitations. The approach turns an overwhelming microscopic problem into something that can actually be studied. Phonons are especially important because vibrations influence far more than the sounds we hear. They play a major role in how heat travels through many solids. They interact with electrons and affect electrical resistance. They are involved in important explanations of conventional superconductivity. They influence how materials respond to light and other forms of energy. A concept that begins with something as familiar as vibration quickly connects to some of the central questions in modern material science. Yet none of that changes the immediate experience you are having while listening. Your ears are receiving an ordinary sound wave. The pressure near you is changing by tiny amounts. Your auditory system is responding to those changes, and your brain is reconstructing speech from them. Unless you happen to be listening inside an unusually sophisticated low-temperature quantum laboratory, there is no reason for the quantum nature of this sound to feel obvious. That difference between what we experience and what physics describes underneath is part of what makes the subject so interesting. Nature does not owe us an intuitive microscopic picture. Human senses evolved to deal with objects, voices, movement, predators, food, weather, other people, and the practical problems of staying alive. They did not evolve to show us quantized normal modes of a crystal lattice. The fact that we can discover those things anyway is one of the more impressive consequences of having brains that refuse to leave simple questions alone. And the simple question remains with us. What is sound, really? At the everyday scale, it is organised mechanical motion travelling through matter. At the quantum scale, that motion can be described in terms of quantised excitations. The material matters, the collective pattern matters, the amount of energy matters, the scale of observation matters. The word sound turns out to cover several levels of description at once, from the pressure wave moving through a room to the microscopic vibrations occurring inside matter. To understand how those levels fit together, we need to begin with the part that seems most familiar and make it precise. Before asking what a phonon is, we need to understand what a vibration is actually doing inside a material, why the disturbance travels when the particles themselves mostly remain near their original positions, how pressure changes become waves, and why different materials carry those waves in different ways. Once that ordinary mechanical picture is clear, the quantum version will have something solid to build on, and that takes us naturally to the classical story of vibrations and waves. To understand what quantum physics eventually adds to the story of sound, it helps to begin with the version that works perfectly well for almost everything we hear in ordinary life. Long before anyone spoke about phonons, quantum states, or microscopic excitations, people could already observe that sound had something to do with movement. Strike a bell and the metal vibrates. Pluck a string and it moves back and forth. Tap the side of a glass and the glass trembles slightly while producing a tone. Place your fingers gently against your throat while speaking, and you can feel vibration there as well. The connection seems obvious once you notice it. Sound begins when something moves repeatedly, but the interesting part is what happens next, because the object producing the sound usually stays where it is, while the sound itself travels across the room. Imagine a loudspeaker playing a low musical note. The surface of the speaker moves forward and backward very quickly. When it moves forward, it pushes on the air immediately in front of it. The molecules in that region are forced slightly closer together than usual. That creates an area of higher pressure. Those molecules then push against molecules nearby, which push against others, and the region of increased pressure begins to move outward. When the speaker moves backward, it leaves slightly more room in front of itself, creating a region where the air molecules are spread a little farther apart. That creates lower pressure as the speaker continues moving forward and backward, alternating regions of higher and lower pressure spread away from it. This travelling pattern is what we call a sound wave in air. The air itself is not flowing from the speaker all the way to your ear. Individual molecules move around constantly because air is warm, but the motion associated with the sound wave is mostly a small back and forth movement around their usual positions. The pattern of compression moves forward, even though the molecules carrying it do not travel forward with the sound over the same distance. This can feel strange at first because we're used to thinking that if something travels, some material object must travel with it. A wave shows us that a pattern can move through matter without the matter itself making the entire journey. A familiar example is a ripple moving across water. If you watch a floating leaf while a small wave passes beneath it, the leaf does not necessarily travel across the pond with the wave. It may rise, fall, and shift slightly while the ripple continues onward. The water participates in the movement, but the travelling shape and the individual pieces of matter are not doing exactly the same thing. Sound follows the same broad idea, although sound waves in air involve pressure changes moving through the gas rather than visible humps moving across a surface. Another useful comparison is a long spring. If you compress a few coils at one end and release them, the compressed region can travel along the spring. Each section moves only a short distance, but the disturbance can move much farther. Air behaves somewhat like an enormous three-dimensional version of that idea. There are no literal springs connecting the molecules, but the molecules interact through collisions and forces. If one region is compressed, it tends to expand again, affecting neighbouring regions in the process. That combination of inertia and restoring behaviour allows a wave to propagate. This gives us the first important piece of the classical story. Sound is not a substance being carried from one location to another. It is a moving disturbance in a material. That material is usually called the medium. Air can be a medium for sound. Water can be a medium. Wood, metal, glass, rock, and many other materials can carry sound as well. The details change because the particles inside those substances are arranged differently and interact differently, but the basic requirement remains. There must be something capable of responding to mechanical disturbance. This is why ordinary sound does not travel through a perfect vacuum. If there are no particles to move and no material interactions to pass the disturbance along, the wave has no medium. A ringing alarm clock placed inside a container will become quieter as the air is removed from around it. The clock can still vibrate, but less and less of that vibration can be transferred through the remaining gas. Eventually, with very little matter present, almost no ordinary sound reaches the outside through that route. The vibration exists at the source, but there is no effective chain of particles available to carry the pressure disturbance across the empty region. Inside solids, the situation is different from air, but follows the same general logic. Atoms in a solid are held in relatively stable positions by interactions with neighbouring atoms. They are not completely motionless. Even in an apparently rigid object, atoms are moving. If one region of the material is disturbed, the atoms there shift from their usual positions. The forces connecting them to neighbouring atoms tend to pull or push them back, and those neighbours respond in turn. The disturbance can therefore move through the solid. Because atoms in many solids interact strongly and sit much closer together than molecules in a gas, sound often travels faster through solids than through air. The exact speed depends on the material. A material that strongly resists being compressed can transmit a disturbance efficiently, while density also affects how easily the particles respond to force. The balance between those properties determines how quickly a sound wave moves. This is why pressing your ear against a solid object can sometimes let you hear a vibration before the same sound reaches you through the surrounding air. You can experience a simple version of this with a long table. If someone gently taps one end while you place your ear against the other, part of the vibration travels through the table itself. The molecules and atoms in the solid transfer the disturbance efficiently. The sound you hear through the wood is not identical to what you would hear through the air because the material transmits different frequencies with different effectiveness. The table changes the sound while carrying it. Frequency is one of the central ideas in understanding what we hear. When something vibrates, we can ask how rapidly the motion repeats. A slow vibration has a low frequency. A rapid vibration has a high frequency. Our ears interpret much of this difference as pitch. Lower frequencies are usually heard as lower tones, while higher frequencies are heard as higher tones. A large bass speaker moving back and forth relatively slowly can produce the low notes that you may feel as much as hear. A small vibrating source moving very rapidly can produce much higher notes. The important thing is that pitch is our perception, while frequency describes the physical repetition of the wave. They are closely related, but they are not exactly the same concept. Your auditory system takes incoming pressure variations and processes them. The brain then constructs the experience of pitch. Different combinations of frequencies can produce rich and complicated sounds, which is why a violin and a piano can play what we identify as the same musical note while still sounding obviously different. The reason is that real musical sounds are rarely made from one simple vibration. A string, a column of air, a drum membrane, or a human voice can vibrate in several patterns at once. Along with a main frequency, additional frequencies can be present. These contribute to the quality or character of the sound. Musicians often speak of tone or timbre when describing this difference. Physics describes the underlying pattern in terms of the mixture of frequencies and the way their strengths change over time. Consider a guitar string. When you pluck it, the entire string can move in one broad pattern, but smaller sections of the string can also participate in faster patterns of motion. The result is not a single perfectly simple vibration. Several modes are excited together. The wooden body of the guitar responds to the string. The surrounding air responds to the guitar. The room itself adds reflections. By the time the sound reaches your ear, what began as one pluck has become a complicated collection of waves. A mode is simply a particular allowed pattern of vibration. This idea becomes extremely important later when quantum physics enters the story, because quantization applies naturally to these vibrational modes. For the moment, though, we can understand them classically. If you shake a rope fixed at one end, some patterns fit naturally along its length while others do not remain stable. A string on a musical instrument behaves similarly. Its length, tension, and mass help determine which patterns of vibration can persist. Objects therefore have natural ways they prefer to vibrate. Strike a metal object, and you may excite several of those natural modes at once. A small spoon produces a different collection of vibrations from a large bell because its size, shape, material, and structure are different. A wine glass has its own preferred patterns, a bridge has its own, a building has its own. Even the air inside a room has patterns that can be reinforced depending on the room's dimensions. When a driving vibration matches one of these natural patterns especially well, resonance can occur. The response becomes much stronger than it would at other frequencies. You may have noticed this when a particular bass note causes something in a room to rattle while nearby notes do almost nothing. A shelf, window, picture frame, or loose object may happen to have a natural vibration close to the frequency being played. Energy is transferred into that motion efficiently, and suddenly the object decides to join the performance without being invited. Resonance is not only a musical curiosity, it matters throughout engineering and physics. Machines vibrate, vehicles vibrate, buildings vibrate, aircraft components vibrate. Engineers must understand these natural modes so that repeated forces do not accidentally drive structures into damaging motion. At smaller scales, the same general idea of allowed vibrations appears inside materials, and there it begins to connect directly to the quantum description we are working toward. Sound waves can also interact with one another. If two disturbances pass through the same region, their effects combine. Sometimes they reinforce one another, sometimes they partially cancel. This is called interference. You may hear this when two similar tones are played together and the loudness seems to rise and fall. Noise-cancelling headphones make use of the same broad principle. They detect some of the incoming sound and produce another sound arranged so that the pressure variations reduce one another near the ear. No air molecules are being persuaded to stop existing. Instead, the patterns of pressure are being combined. Where one wave produces increased pressure while another produces a corresponding decrease, the total disturbance can become smaller. It is another reminder that sound is fundamentally about organized motion, rather than a stream of material particles being delivered to you. Sound can also reflect. When a traveling wave reaches a boundary, some of its energy may return in another direction. An echo is one obvious result. Sound travels toward a distant surface, reflects, and returns after a delay. In a large empty room, reflections can continue bouncing between surfaces, creating reverberation. Soft materials such as curtains, carpets, and upholstered furniture can absorb more sound energy than hard walls, which is why the acoustic character of a furnished room can be so different from the same room when it is empty. Some sound energy can also pass through a boundary. A wall may reflect part of a sound, absorb part of it, and transmit part of it into the material and eventually into the air on the other side. Anyone who has lived beside a noisy neighbour has probably conducted this experiment extensively without intending to contribute to acoustics. As sound travels, its energy tends to spread over a larger region, so its intensity decreases with distance. Energy can also be lost from the organised wave into less organised microscopic motion within the material. In everyday language, some of the sound is absorbed. The energy has not simply vanished, it has been redistributed, often becoming thermal motion. A soundproofing material works partly by making it difficult for coherent vibrations to continue travelling efficiently. The organised wave becomes scattered and dissipated through many microscopic motions. This is already bringing us closer to the level where the classical picture starts to reveal what it leaves unexplained. Classical acoustics can describe the wave beautifully. It can tell us how frequency relates to vibration, how waves reflect, interfere, resonate, and travel through materials. It can predict what happens when sound crosses boundaries. It can explain why a small room sounds different from a cathedral, and why a tuning fork produces a relatively pure tone, while a cymbal produces a much more complicated collection of frequencies. But classical physics treats the energy in these vibrations as though it can vary smoothly without any fundamental step size. You can imagine making a wave weaker and weaker, then weaker again, without encountering a smallest unit associated with that vibrational mode. At the scales of ordinary sound, this works so well that there is usually no reason to question it. Suppose you slowly reduce the volume of a speaker. The motion of the speaker becomes smaller. The pressure variations become smaller. The sound becomes quieter. Nothing obvious happens that suggests the energy is divided into individual pieces. Eventually the sound becomes too faint for your ear to detect, but that says more about the sensitivity of your hearing than it does about whether nature itself has become discontinuous. For a long time, that smooth picture seemed entirely natural. Waves were waves. Matter might be made of particles, but the energy carried by a classical vibration could be treated as continuous. The development of quantum theory forced physicists to reconsider that assumption. It turned out that microscopic oscillating systems do not possess energy in every arbitrary amount allowed by classical reasoning. The permitted behavior comes in quantum states. Before reaching that point, it is worth noticing how much of sound can already be understood without quantum mechanics. If you clap your hands, you create a rapid disturbance in the air. That disturbance spreads outward. If it encounters a wall, some of it reflects. If the room is large enough, you may hear the reflection separately as an echo. If you move into a room full of curtains and furniture, more of the sound is absorbed and scattered, so the echo becomes less obvious. If you clap underwater, the disturbance travels differently, because water has different physical properties from air. If you tap a metal rail, the vibration can move efficiently through the solid. The same framework explains speech. Your lungs provide airflow. Structures in your larynx vibrate. Your throat, mouth, and nasal cavities modify the resulting sound by reinforcing some frequencies more than others. Your tongue and lips continually change the shape of the system. What begins as vibration becomes a remarkably complex pressure pattern. Another person's ear receives that pattern, and the auditory system separates and interprets enough of its structure to recover language. There is no little packet marked with the word hello travelling intact from one person to another. The meaning is encoded in a changing physical pattern. The pattern can be converted into an electrical signal by a microphone, stored digitally, transmitted across a network, turned back into electrical activity in a speaker, converted into pressure variations again, and finally interpreted by a listener. The physical carrier can change while the structure of the information remains recognizable. This is one reason sound is such a useful bridge into deeper physics. It shows how important patterns can be. The individual air molecules are not the message. Replace those molecules with others, and the spoken word can still be transmitted. What matters is the organized disturbance passing through them. In a solid, the atoms provide the medium, but the vibrational mode belongs to the collective system. That collective character becomes especially clear if we imagine a perfectly ordered row of identical atoms in a crystal. Each atom sits near an equilibrium position, held there through interactions with its neighbours. Disturb one atom, and it begins to move. Its neighbours respond. A wave can travel through the arrangement. Classical physics would describe the displacement of the atoms and the resulting wave. It would identify different allowed patterns of vibration and assign energy to them. Now make the system very small, very cold, or examine it with enough precision that quantum effects cannot be ignored. The atoms are no longer adequately described as tiny classical masses attached by imaginary springs. Their possible states are governed by quantum mechanics. The vibrational modes still exist, but the amount of energy associated with them no longer behaves exactly as the classical picture suggests. This is where the familiar story of sound begins to change character. Nothing suddenly stops vibrating. Waves do not disappear. The classical description does not become useless. Instead, we discover that the smooth wave was an approximation emerging from a deeper structure. Much as a photograph can look continuous from across the room, but reveal individual pixels when examined closely, a classical vibration can appear smoothly variable, while its quantum description involves discrete changes in excitation. The comparison is not exact, because phonons are not literal pixels of sound, but it points us toward the right question. If a material has a particular vibrational mode, and quantum mechanics restricts the allowed energy of that mode, what does it mean when one unit of vibrational excitation is added or removed? How can something spread across many atoms behave as though it were a particle? And why would physicists find it useful to give that collective excitation its own name? Those questions take us away from the broad movements of speakers, strings and air pressure, and toward the microscopic motion inside matter. The wave remains, but our description of what the wave can contain is about to become much more specific, because once the vibration itself is treated quantum mechanically, sound begins to acquire a particle-like language that classical acoustics never needed. The classical picture of sound takes us a surprisingly long way. A vibrating object disturbs the material around it. Those disturbances move through the medium, and a pattern of changing pressure or displacement travels from one place to another. That description can explain conversations, musical instruments, echoes, room acoustics, ultrasound, and the irritating ability of a low bass note to find the one loose object in your house that you did not know could rattle. For most everyday purposes, nothing more complicated is needed. Yet the moment we start asking what happens inside matter at very small scales, the classical picture begins to leave out something important. The atoms carrying the vibration are quantum objects, and once their motion is treated according to quantum mechanics, the energy of the vibration cannot always be described as a perfectly smooth quantity that can take any value we please. This change is easier to understand if we begin with something simpler than an entire sound wave. Imagine a small object that can move back and forth around a resting position. A weight attached to a spring is the usual example. Pull it slightly and let go, and it oscillates. In classical physics, there is no fundamental restriction on how much energy that oscillation may have. It can move strongly, weakly, or by any amount in between. If you wanted to reduce the vibration gradually, classical physics would allow you to keep reducing its energy without ever meeting a smallest permitted step. Make the motion half as large, then smaller again, then smaller again, and nothing in the classical description tells you to stop. Microscopic systems do not behave quite like that. When quantum mechanics is used to describe an oscillator, the possible energies are restricted. Instead of every imaginable value being available, the system occupies particular allowed energy states. Moving from one permitted state to another involves gaining or losing a definite amount of energy. This is what physicists mean when they say that the vibration is quantized. The word can make the idea sound more mysterious than it needs to be. It simply means that, for the particular mode we are describing, changes in vibrational energy occur in units, rather than through every possible intermediate value. A familiar comparison is a staircase. On a smooth ramp, you can stand at any height along the slope. On a staircase, there are particular levels where your feet can rest. Quantum energy states are not literally tiny stairs inside an atom, but the comparison captures the important difference between continuous and discrete possibilities. Classical physics often gives us something like the ramp. Quantum mechanics reveals something more like separate allowed levels. Now take that idea and apply it not to one isolated oscillator, but to a material containing enormous numbers of atoms. In a solid, atoms are arranged close together and interact strongly with their neighbours. If one atom moves slightly, the forces between atoms affect the next one, which affects another, and coordinated vibrations can spread through the structure. As we saw earlier, these vibrations can be described as modes, particular patterns in which the material can move. Each mode behaves in some ways like its own oscillator. Quantum mechanics therefore tells us that the energy stored in that vibrational mode comes in discrete amounts. When one unit of excitation is present in the mode, physicists describe that excitation as one phonon. Add another unit and we can describe the mode as containing another phonon. Remove one unit and one phonon has been absorbed or destroyed. This is the point where sound enters the quantum world. It is also the point where language can easily lead us into the wrong mental picture. Calling a phonon a particle of sound is convenient, but if we imagine a tiny solid object bouncing between atoms, we have already gone astray. A phonon is not a miniature ball hidden inside the material. It is a quantum of collective vibration. The motion belongs to the material as a whole, or at least to a large collection of its atoms, and the phonon is a way of describing one discrete excitation of that collective motion. Think about a wave moving through a crowded stadium. No individual person is the wave. The wave exists because many people participate in a coordinated pattern. If everyone disappears, there is no stadium wave left floating above the empty seats. A phonon has something of this collective character. It only makes sense in relation to the material whose atoms are participating in the vibration. This is why physicists describe phonons as quasi-particles rather than fundamental particles. Electrons are fundamental particles as far as current physics can tell. You can remove an electron from one material and place it somewhere else. A phonon does not have that sort of independent existence. It is an excitation of a particular material system. No material, no vibrational mode, and therefore no phonon belonging to that mode. The word quasi-particle sometimes sounds as though the particle is somehow less real. It would be understandable if the name made you imagine a physicist clearing their throat and saying that the particle is only mostly a particle on weekdays. But quasi-particles are extremely useful physical concepts. They can carry energy through materials, interact with other excitations, scatter from defects, be created, be absorbed, and produce effects that can be measured experimentally. They are real features of the behavior of many body quantum systems, even though they are not elementary building blocks of the universe. Phonons become especially useful in crystals. A crystal has atoms arranged in a repeating structure, which means its collective vibrations can be organized into well-defined modes. Instead of trying to calculate the motion of every individual atom separately, physicists can describe the possible vibrational patterns and then talk about the quantum excitations of those patterns. This turns what would otherwise be a horrifying bookkeeping exercise involving an enormous number of interacting atoms into a much cleaner physical description. Suppose you have a crystal containing more atoms than you would ever want to count individually. Even a very small piece of solid material contains an astonishing number. Each atom can move in several directions, and its motion is coupled to the motions of neighbouring atoms. If you try to follow every detail directly, you would quickly end up with an enormous collection of interconnected motions. Mathematically, it is possible to reorganize that complicated problem into collective modes. Each mode represents an organized pattern of vibration. Quantum mechanics then tells us how those modes can be excited. A phonon is associated with one unit of excitation in one of those modes. Notice how different this is from saying that a particular atom contains a phonon. The phonon belongs to the pattern. Many atoms may participate in that pattern. Asking which atom the phonon is inside can be a little like asking which individual person in a stadium contains the audience wave. The question assumes the wrong kind of object. This also helps explain why phonons can appear to move through a material. The vibrational excitation can propagate from one region to another, carrying energy with it. We can describe that propagation using phonons in much the same way that we describe other particle-like excitations moving through a system. Yet underneath that description, atoms are responding collectively to one another. If all this sounds rather removed from the sound coming from your headphones or speakers, that is because ordinary audible sound contains an enormous amount of collective activity. The quantum units are usually so numerous that the smooth classical wave becomes an excellent approximation. Your ear does not receive one phonon and announce that a quantum event has occurred. Everyday sounds involve huge numbers of microscopic excitations and interactions, and the combined result behaves in the familiar continuous way described by acoustics. This relationship between the quantum and classical descriptions appears throughout physics. Light is a useful comparison again. A weak enough light field can reveal effects associated with individual photons, but a bright lamp does not look like a swarm of separate flashes arriving one at a time. There are so many photons involved that the overall electromagnetic field can often be treated in a smooth classical way. With vibration, a similar transition occurs. Individual phonon behavior may matter in carefully controlled systems, while a loudspeaker producing music is comfortably described using classical pressure waves. There is an important difference, however, because the phonon is tied to the material. A photon can leave a star and travel through empty space for years before interacting with matter. A phonon cannot leave a crystal and continue through vacuum as the same independent excitation. If vibrational energy reaches the surface of a material, it may be converted into another form. It might generate an ordinary sound wave in the surrounding air. It might interact with light. It might contribute to heat. But the phonon itself is defined through the collective behavior of the material that supports it. This gives us a better way to think about what happens when you strike a solid object. Suppose you tap a metal bar. At the large scale, the bar vibrates and produces sound waves in the surrounding air. Classical physics describes this very well. At a microscopic level, however, the internal vibrational energy of the solid can be described using phonons. Those phonons move through the structure, interact with one another, scatter from imperfections, and exchange energy with other parts of the material. Some of that vibrational motion at the surface couples to the air. The surface pushes against nearby air molecules, producing the pressure variations that travel toward your ear. The sound wave in the room and the phonons inside the solid are related, but they are not simply the same object moving unchanged across the boundary. The description depends on the system through which the energy is travelling. This is one reason the phrase sound particle needs care. In popular descriptions of quantum physics, we often want a neat parallel. Light has photons, so perhaps sound has phonons. There is truth in that comparison, but it can hide the important differences. A photon is a quantum of the electromagnetic field. A phonon is a quantum of a collective vibrational mode in matter. One is associated with a fundamental field. The other emerges from the behavior of many particles acting together. The idea of emergence is going to return often as we move deeper into quantum sound. Nature contains many situations in which a large collection of simple components produces something that is useful to describe as a new object. A wave is one example. Temperature is another. No individual atom in a cup of tea has the temperature of the entire cup. Temperature summarizes the statistical behavior of enormous numbers of microscopic particles. In a similar way, a phonon describes collective motion rather than one atom acting alone. There is another detail that separates quantum vibration from the simple picture we might expect. Even if we remove all phonons that can be removed from a vibrational mode, quantum mechanics does not allow the system to become perfectly motionless in the classical sense. The lowest possible state of a quantum oscillator still has what physicists call zero-point motion. The atoms retain unavoidable quantum fluctuations even at the minimum possible energy of the mode. This is an important feature of quantum mechanics. The ground state, meaning the lowest energy state, is not equivalent to a classical object sitting completely still with no motion at all. Quantum uncertainty prevents that perfectly motionless picture. So even in an idealized material cooled as far as physically possible, microscopic vibrations do not simply vanish into absolute stillness. That does not mean you would hear a constant background noise coming from zero-point motion. Hearing requires the right kind of energy transfer into your auditory system, and the ground state does not provide an unlimited source of audible sound. It means that the quantum mechanical description of a vibrating system never becomes identical to the classical image of atoms frozen perfectly in place. Temperature adds another layer. At ordinary temperatures, atoms in materials are constantly being thermally excited. Many vibrational modes contain phonons simply because thermal energy is available. The warmer the material becomes, the more strongly many of these modes can be populated. This is closely connected to how solids store and transport heat. What we casually call heat inside a solid often involves enormous numbers of microscopic vibrations. Phonons can carry thermal energy through the material. They move, scatter from one another, interact with defects, and eventually redistribute energy. That means the same quantum concept used to discuss sound is also central to understanding why some materials conduct heat well, while others are good insulators. Diamond, for example, can carry vibrational energy very efficiently because of its crystal structure and strong atomic bonds. Other materials scatter phonons much more readily, limiting the flow of heat. Engineers can manipulate material structures specifically to change how phonons move. The quantum physics of sound therefore becomes part of the physics of thermal management in electronics, materials design, and many technologies that may not seem to have anything to do with hearing. Phonons also interact with the electrons. When an electron moves through a material, it can disturb the atomic lattice. Likewise, vibrations of the lattice can affect how electrons move. These interactions contribute to electrical resistance in ordinary conductors. As temperature changes and the population of phonons changes, the electrical behavior of a material can change as well. There is an even more remarkable example in conventional superconductors. In these materials, interactions involving lattice vibrations help electrons form correlated pairs. Those paired electrons can then participate in a superconducting state, in which electrical resistance disappears under suitable conditions. Sound-like vibrations inside the material are therefore involved in one of the strangest and most useful collective quantum effects we know. That is quite a promotion for something that began with a vibrating guitar string. The story becomes stranger when scientists deliberately create systems in which individual phonons can be controlled. At everyday temperatures and sizes, there are usually far too many thermal vibrations for a single quantum excitation to stand out clearly. Researchers can overcome this by making mechanical systems extremely small and cooling them to very low temperatures. Reducing the temperature suppresses many thermal phonons, making the underlying quantum behavior easier to observe. Tiny mechanical resonators can then behave like quantum oscillators. Scientists can prepare them near their lowest energy state, add individual vibrational excitations, couple them to microwave or optical systems, and measure how those excitations behave. In such experiments, a single phonon is not merely a mathematical convenience. It becomes a controllable unit of energy in a real device. This has led to an area often called quantum acoustics. Researchers study sound and mechanical vibration under conditions where their quantum properties are directly important. They can investigate how individual phonons interact with quantum bits, how vibrational excitations can transfer quantum information, and how mechanical systems might connect different kinds of quantum technology. The word acoustics may make you imagine concert halls, microphones, and someone tapping a tuning fork, but quantum acoustics often involves devices so small that the vibration would never be heard directly by a human ear. The connection is still sound in the physical sense of mechanical excitation, but the experiments operate at scales where our senses are not useful instruments. It is also possible to work with frequencies enormously higher than ordinary hearing. Humans can hear only a limited range, and that range usually becomes narrower with age. A phonon does not care about the career limitations of the human auditory system. Vibrational excitations can occur across a much wider range of frequencies, including frequencies that would be completely inaudible, even if they somehow reached your ear in the appropriate form. This is why it is better to think of phonons as quanta of vibration, rather than simply tiny pieces of audible sound. Audible sound is one familiar region of a much larger subject. The same principles describe vibrations involved in heat flow, microscopic material behavior, and quantum devices. There is also a surprising question hiding in the phrase one phonon. If a phonon is a collective excitation spread across many atoms, how can we call it one thing at all? This question touches a deeper feature of quantum physics. A quantum object does not need to resemble a tiny localized classical object in order to behave as a single excitation. What makes something count as one quantum is the structure of the state and the amount of excitation associated with it, not whether we can draw a small circle around it and say that everything inside the circle belongs to the particle. Quantum physics repeatedly forces us to loosen the connection between particle and tiny ball. Electrons have wave-like properties. Photons can form interference patterns. Quantum states can extend across regions of space. Phonons fit comfortably into this less familiar world because they are particle-like excitations of waves from the beginning. At large scales, these distinctions become difficult to notice because countless quanta combine. A musical note in a room behaves as a classical sound wave because enormous numbers of microscopic degrees of freedom participate. The pressure rises and falls smoothly enough that classical equations describe the result with extraordinary accuracy. Quantum mechanics remains underneath, but its discrete structure has been averaged into something that appears continuous. You can compare this with watching a digital screen from across a room. The image appears smooth. Move close enough and individual pixels become visible. Yet the picture at normal viewing distance was not false. It was simply a useful large-scale description created by many smaller elements working together. A classical sound wave is similar in spirit. It is not an illusion that quantum physics later corrects. It is an emergent description that becomes extremely accurate when vast numbers of quantum excitations participate. There is one warning worth keeping in mind with that comparison. Phonons are not fixed little blocks from which every sound is assembled in the same way pixels build a screen. The number of phonons depends on the vibrational state and on how we choose the appropriate modes of the material. The quantum description is based on the possible collective oscillations of the system, not on a universal collection of identical sound grains hidden everywhere. This becomes especially interesting when materials have complicated structures. Different vibrational modes can behave very differently. Some involve neighbouring atoms moving together, others involve different groups of atoms moving against one another. Some vibrations can travel through a material efficiently, while others remain more localized. The structure of the material determines which modes exist and how their phonons behave. A simple crystal may therefore have several families of vibrational excitations. Some resemble the long wavelength sound waves we know from classical acoustics. Others involve microscopic patterns that have no direct everyday equivalent. Physicists still use the language of phonons for both because they arise from quantized lattice vibrations. Once that distinction is understood, the quantum world of sound becomes much less mysterious. We did not discover that ordinary sound secretly consists of tiny flying balls. We discovered that the collective vibrations producing and carrying mechanical energy have quantum states. Changes in those states occur in discrete units, and those units can be treated as quasi-particles called phonons. That description allows physicists to follow vibrational energy through matter with remarkable precision. A phonon can be generated when a system loses energy into a vibrational mode. It can be absorbed when that energy is transferred somewhere else. Phonons can scatter from one another or from impurities. They can interact with electrons and photons. Under carefully controlled conditions, scientists can manipulate them individually. The ordinary sound around you is therefore sitting on top of an immense microscopic activity that your ears never reveal. A voice remains a smooth voice. Music remains music. The soft hum of a fan remains an excellent reminder that you should probably not start dismantling the fan to investigate its vibrational modes before going to sleep. Yet beneath the familiar pressure wave is a material world in which vibration obeys quantum rules. To see why physicists are willing to treat these collective excitations so much like particles, The next step is to look much more closely at the phonon itself. We need to understand how something that is not a fundamental particle can still carry definite amounts of energy, move through a material, collide with other excitations, appear and disappear, and become one of the most useful objects in the quantum physics of matter. By now, the word phonon has appeared often enough that it deserves a proper introduction. We have described sound as a vibration moving through matter, and we have seen that quantum mechanics changes the way those vibrations can store and exchange energy. The next step is to look carefully at the object physicists use to describe that quantum behaviour. A phonon is often introduced with the wonderfully convenient phrase quantum particle of vibration. That phrase is not wrong, but it can create a very misleading picture if we take the word particle too literally. There is no tiny bead of sound hiding between the atoms of a crystal. A phonon is not a microscopic grain that you could remove with tweezers, place on a table, and examine under a very ambitious microscope. It is something much more interesting. A phonon is a single quantum excitation of a collective vibration in matter. To see why such an idea is useful, imagine a row of atoms inside a solid. In reality, a solid contains an enormous number of atoms arranged in 3 dimensions, but a simple row gives us something manageable to picture. Each atom sits near a preferred position because it interacts with its neighbours. If one atom is pushed slightly to one side, those interactions encourage it to move back toward its original position. During that motion, it also affects the atoms beside it. The disturbance can therefore spread through the row. One atom moves, then another responds, then another, and before long the material contains an organised pattern of vibration. In classical physics, we could describe that pattern by following how far each atom moves and how the displacement changes with time. If the material contains only a few atoms, that might be manageable. If it contains trillions upon trillions of atoms, the calculation becomes much less appealing. One could theoretically keep track of every atomic movement, but this would be like trying to understand traffic in a city by recording the exact movement of every piston inside every car engine. The information would be there, but the useful pattern would be buried underneath it. Physicists therefore reorganize the problem. Instead of focusing on every atom separately, they identify collective patterns in which many atoms move together. These patterns are called vibrational modes. A mode is simply one of the natural ways the material can vibrate. Some modes involve neighbouring atoms moving almost together. Others involve more complicated motions in which different groups shift in different directions. Each mode has its own characteristic behaviour, and the material can contain many modes at the same time. This is already familiar from musical instruments. A guitar string does not have only one possible way to move. It can vibrate along its entire length in one broad pattern, while shorter patterns can exist at the same time. Those additional modes help give the instrument its characteristic sound. A bell has many vibrational modes. So does a glass, a drum, a metal plate, and the air inside a room. When you hear a complex sound, you're often hearing the result of many modes being excited together. Inside a crystal, the idea is similar, except now we are dealing with atomic motion rather than something large enough to watch directly. Quantum mechanics tells us that each vibrational mode behaves like a quantum oscillator. Its energy cannot change by every imaginable amount. Energy is added or removed in discrete units. One such unit of vibrational excitation is what we call a phonon. This is the sense in which phonons behave like particles. If a particular vibrational mode gains one quantum of energy, we say that one phonon has been created in that mode. If it gains another, we can describe the mode as containing another phonon. If one quantum of vibrational energy is transferred away, a phonon can be said to have been absorbed or destroyed. This particle language turns out to be remarkably powerful, because it allows complicated patterns of atomic motion to be discussed in terms of individual excitations. The crucial point is that the phonon does not belong to one atom. Imagine a group of people doing a coordinated wave in a stadium. The wave moves around the seats, but no single person is the wave. Each person participates for a moment by standing and sitting, while the pattern continues onward. If someone asked which spectator the wave was located inside, the question would miss what the wave actually is. The wave is a collective pattern created by the behavior of many people. A phonon has a similar relationship to the atoms in a material. Many atoms participate in the vibration. The phonon describes the quantum excitation of that collective pattern. This is why phonons are called quasi-particles. They behave like particles in many useful ways, but they are not fundamental particles that exist independently of the material. An electron, as far as modern physics knows, is a fundamental particle. You can have an electron moving through empty space. A phonon cannot do that. Remove the material, and the vibrational pattern disappears with it. A phonon needs a medium because it is a property of the medium's collective motion. Asking for a phonon in completely empty space would be rather like asking for a wave in a lake after removing the lake. That does not make phonons imaginary, quite the opposite. Their effects are measurable throughout solid-state physics. They carry energy, they influence heat flow, they scatter from defects, they interact with electrons and with other phonons. Under carefully controlled conditions, scientists can even create and detect individual phonon excitations. The fact that they arise from collective behavior rather than existing as elementary particles does not make them less physically meaningful. The idea of a quasi-particle appears in many areas of physics, because nature often becomes easier to understand when collective behavior is given a particle-like description. Materials contain enormous numbers of interacting components, and the direct microscopic description can become overwhelmingly complicated. If those interactions naturally produce stable patterns, physicists can often treat the patterns as objects in their own right. It is a little like describing a storm. A hurricane is made from countless air and water molecules, none of which individually contains the hurricane. Yet the storm has a location, direction, speed, structure, and life cycle that can be studied without tracking every molecule separately. A phonon is vastly smaller and governed by quantum mechanics, but the general lesson is similar. Collective organization can become a useful physical entity. One reason phonons are particularly important is that vibrations exist almost everywhere inside solids. Atoms are not frozen motionless in place. At ordinary temperatures, they are constantly moving around their equilibrium positions. Thermal energy excites many vibrational modes, and those excitations can be described using phonons. A warm solid contains a complicated population of them. This gives phonons a major role in heat. When one end of a solid object is heated, the atoms in that region gain energy and vibrate more strongly. That vibrational energy can spread through the material. In many non-metallic solids, a large part of this energy transport can be understood as phonons moving and interacting. The way phonons travel, therefore, helps determine how efficiently a material conducts heat. Consider a crystal in which the atoms are arranged very regularly. A phonon moving through such a structure can sometimes travel a considerable distance before being scattered. Now introduce defects, impurities, or boundaries into the material. These disturbances can scatter phonons and make it harder for vibrational energy to travel. This is one reason the microscopic structure of a material can strongly influence its thermal properties. Engineers can take advantage of this. By changing the composition or internal structure of a material, they can alter how phonons move through it. This matters in electronics, where unwanted heat must often be removed from very small components. It matters in thermal insulation, where the goal may be exactly the opposite. A surprisingly large amount of practical engineering therefore depends on controlling collective atomic vibrations that no human being could ever hear. Phonons also interact with electrons, and this relationship has consequences for electrical resistance. When electrons move through a solid, they do not travel through a perfectly quiet background of motionless atoms. The lattice is vibrating. Electrons can scatter from those vibrations, changing their motion. As temperature rises, the population of thermal phonons often increases, giving electrons more opportunities to scatter. In many ordinary metals, this contributes to the increase in electrical resistance that occurs as the material becomes warmer. The interaction can do something even more remarkable under special conditions. In conventional superconductors, lattice vibrations help create an effective attraction between electrons. Those electrons can form correlated pairs and participate in a collective state that carries electrical current without ordinary resistance. The details are subtle, but the important point for our story is that phonons are not merely an interesting way to talk about sound. They can help determine how electricity behaves inside matter. There is another feature that makes phonons unusual compared with the particles we encounter in introductory physics. The number of phonons in a material is not fixed. A piece of matter does not come with a permanent inventory of phonons, in the way it contains a certain number of atomic nuclei. Phonons can be created when energy enters a vibrational mode and removed when that energy is transferred elsewhere. Suppose an energetic electron moves through a crystal and loses some of its energy to the lattice. That energy can appear as additional vibration. In the quantum description, one or more phonons may have been created. Later, those phonons may interact with other excitations, transfer their energy, or combine into different vibrational activity. The phonon number changes because phonons are excitations rather than permanent constituents of matter. Light offers another helpful comparison. A light source can create photons and a detector can absorb them. The number of photons present in a region changes constantly. Something similar happens with phonons inside a material. They can appear and disappear as energy moves between different parts of the system. Once again, though, the comparison should not tempt us into thinking that phonons are simply sound versions of photons. Their physical origins are different. A photon belongs to the electromagnetic field and can propagate through vacuum. A phonon belongs to a collective vibrational mode of matter. When a phonon reaches the surface of a solid, it cannot simply leap into empty space and continue as the same object. Its energy may be transferred into another system. If the solid touches air, the vibration at its surface may create a pressure wave in the air. If the material is coupled to another solid, vibrational energy may cross the boundary. Under special circumstances, energy can also be exchanged with light, but the identity of the excitation depends on the physical system supporting it. This helps answer a question that often appears when phonons are first introduced. If you're listening to music through a speaker, are phonons flying from the speaker into your ear? Not in the simple way that statement suggests. Inside the solid components of the speaker, vibrations can indeed be described using phonons. At the surface of the speaker, the moving material pushes and pulls on the surrounding air. In air, the sound is carried by changing pressure and molecular motion. When the sound reaches your ear, it causes structures there to vibrate. Different descriptions are useful in different parts of the process. The energy continues through the system, but we should not imagine one phonon starting deep inside the loudspeaker, travelling through the air, entering your ear, and announcing its arrival. Phonons are defined relative to the vibrational modes of particular material systems. There is a further subtlety. We have been talking about phonons as though they can move through a material, and that language is useful. Yet the motion is again not like a tiny ball travelling between atoms. What moves is the excitation associated with the collective vibrational pattern. The atoms themselves remain close to their normal positions, while the energy and phase of the disturbance propagate through the structure. This is similar to our classical description of sound, but quantum mechanics changes what can be said about the excitation. Instead of describing only a smooth wave carrying an arbitrary amount of energy, we can talk about individual quanta associated with the vibrational mode. At the scale of ordinary sounds, the number of phonons involved is usually enormous. That is why you do not notice the individual quantum units. Imagine looking at a beach from a distant hill. The beach appears to be a smooth band of sand. You cannot distinguish individual grains. Move close enough and the granular structure becomes obvious. A classical sound wave has something of that relationship to the underlying quantum description. The wave appears continuous because so many microscopic excitations contribute that the discrete structure becomes irrelevant to normal observation. The analogy has limits because phonons are not permanently existing grains of vibration, but it captures why classical acoustics work so well. Quantum mechanics does not make classical sound wrong. It explains why the classical description emerges when enormous numbers of quantum events act together. A loud sound corresponds to a large-scale organized vibration, with a great deal of energy compared with the energy of individual quantum excitations. The difference between adding or removing one phonon is then so small relative to the whole that the change is practically invisible. It is like adding one drop of water to a swimming pool and expecting someone standing nearby to notice the rise in water level. If scientists want to observe individual phonons, they therefore need to create very different conditions. One major problem is temperature. At ordinary temperatures, thermal motion fills a material with vibrational excitations. Trying to isolate one additional phonon would be like trying to hear one particular person whispering in the middle of a crowded railway station. There is simply too much background activity. Researchers solve this by cooling systems to extremely low temperatures. As the temperature falls, many thermal vibrations become less active. A carefully designed mechanical resonator can then be brought close to its quantum ground state, where only the minimum allowed vibrational activity remains. Under those conditions, adding one phonon can make a meaningful and measurable difference. The ground state itself contains another distinctly quantum surprise. Classical intuition suggests that the lowest possible energy should correspond to complete stillness. If an oscillator has no energy, surely it should simply sit there doing nothing. Quantum mechanics does not allow that exact picture. Even in the lowest energy state, the oscillator retains unavoidable quantum motion called zero-point motion. This does not mean a frozen crystal should constantly produce audible noise from nowhere. Zero-point motion cannot simply be harvested as an unlimited source of useful energy. It means that quantum uncertainty prevents the atoms from having perfectly definite positions, while also remaining completely motionless. The minimum energy state still contains quantum fluctuations. Once researchers cool a mechanical system close enough to that ground state, they can begin exploring behavior that would normally be hidden. They can deliberately add a single vibrational quantum. They can watch how long it survives. They can allow it to interact with another quantum system. They can transfer energy between mechanical vibration and electromagnetic signals. What would once have sounded like a philosophical claim about whether vibration comes in discrete units becomes an experimental question. This area of research has become important in quantum technologies because phonons can provide a bridge between different physical systems. Some quantum devices operate using microwave signals, others use light, others store information in atoms, defects inside crystals, or superconducting circuits. Mechanical vibrations can sometimes couple to several of these systems, which makes phonons interesting as potential carriers or intermediaries for quantum information. The idea is not that future quantum computers will communicate by playing tiny songs to one another. The vibrations involved may be far outside human hearing and confined to structures much smaller than anything we can see without specialized equipment. The connection to sound is physical rather than musical. These are mechanical excitations of matter, governed by the same broad principles that underlie familiar acoustic waves. The frequencies of phonons can extend far beyond what humans can hear. Our ears respond only to a narrow range compared with the possible vibrational frequencies inside materials. Atoms in a crystal can participate in extremely rapid oscillations. Those high-frequency modes may be completely inaccessible to human hearing, yet they still have quantized excitations that physicists describe as phonons. This is why the phrase particle of sound is best treated as an introduction rather than a complete definition. Phonons are more accurately the quanta of vibrational modes in matter. Sound waves are one familiar manifestation of mechanical vibration, but the phonon concept reaches much further. It applies to the microscopic vibrations that transport heat, influence electrical behavior, interact with light, and contribute to the properties of materials. Different types of vibrational modes also produce different kinds of phonons. In some modes, neighbouring atoms move largely together. producing long wavelength disturbances resembling familiar sound waves. These are called acoustic modes because their behaviour at long wavelengths is closely related to ordinary sound. Other modes involve neighbouring atoms moving against one another in more complicated ways, particularly when the repeating structure of the crystal contains more than one kind of atom, or more than one atom in its basic repeating unit. Those are often called optical modes because of how they can interact with electromagnetic radiation in certain materials. The names can be slightly misleading if taken too literally. Acoustic phonons do not have to be audible, and optical phonons are not particles of light. The labels come from the physical behaviour of the vibrational branches and their historical connection to experiments. What matters is that a solid can support several distinct families of collective motion, each with its own quantum excitations. This makes the interior of a crystal much more active than the everyday appearance of a solid object suggests. Place a crystal on a table, and it looks completely still. At the microscopic level, however, its atoms participate in constant quantum and thermal motion. Vibrational excitations move through the structure. They encounter imperfections, interact with electrons, exchange energy, and influence the measurable properties of the material. The apparently quiet solid is therefore not quiet in the microscopic sense. It contains a complicated landscape of collective motion. Phonons give physicists a way to navigate that landscape. Instead of speaking endlessly about millions of atoms moving slightly to the left while millions of others move slightly to the right, the problem can be reorganized into excitations with identifiable energies and propagation behavior. Once that is done, many calculations begin to look surprisingly particle-like. A phonon travels, it scatters, it is absorbed, another is emitted. Energy and momentum are transferred between excitations. This does not mean the original atoms have disappeared from the story. They are what make the collective vibration possible. The phonon is useful precisely because the underlying atomic interactions produce organised modes that can be treated quantum mechanically. There is something particularly revealing about that idea. We often learn physics as a search for smaller and smaller pieces. Molecules are made from atoms. Atoms contain electrons and nuclei. Nuclei contain protons and neutrons. Protons and neutrons contain quarks. It can create the impression that understanding nature always means discovering what smaller object is hidden inside the larger one. Phonons show us another kind of understanding. Sometimes physics moves in the opposite direction. Instead of looking for a smaller constituent, we look at how many components behave together and discover a new level of description. The phonon is not hidden inside an atom. It emerges when many atoms participate in a collective quantum vibration. That is why quasiparticles are such a powerful idea. Nature can produce effective objects that exist only because a larger system is organised in a particular way. These effective objects can then obey rules of their own, and become the most useful way to understand what the material does. For sound, this means the answer to what is moving becomes richer as we change scales. At the human scale, a pressure wave moves through a room. At the molecular scale, particles move and collide. Inside a solid, atoms shift around equilibrium positions and transfer mechanical disturbance through their interactions. In the quantum description, the collective modes of those motions have discrete excitations, and we call those excitations phonons. All of those descriptions can be correct at the same time. They are simply aimed at different levels of the same physical process. The next question is where the idea becomes especially tangible. If a phonon is one quantum of vibration, can we actually isolate one? Can an experiment create a mechanical system containing a single phonon and then tell the difference between that state and one containing two? More strangely, could anything like a single quantum of sound ever be detected directly? Or are phonons destined to remain useful mathematical language hidden beneath the smooth sounds of everyday life? To answer that, we have to move away from ordinary rooms and ordinary temperatures and look at the remarkably delicate experiments designed to make one quantum of vibration stand out from all the noise around it. Once phonons are introduced as individual quanta of vibration, a very natural question appears. If one phonon represents one quantum of vibrational excitation, could a person ever hear one? Could you sit in a perfectly quiet room, wait patiently, and eventually notice the smallest possible piece of sound arriving at your ear? It is an appealing idea because it would give the quantum world a direct connection to ordinary experience. Instead of learning about microscopic effects through complicated equipment, perhaps we could simply listen carefully enough. Unfortunately, nature has made the situation much less convenient. A single phonon is a meaningful quantum object, but the relationship between one phonon and something we would recognize as an audible sound is not nearly as simple as hearing one tiny click. The first problem is that hearing is a biological process designed for the everyday world. Your ear responds to changing pressure in the air. Those pressure changes move the eardrum, which transfers motion through a set of small bones deeper into the ear. That motion eventually affects fluid and sensory cells, and those cells produce signals that travel to the brain. The entire system is remarkably sensitive, but it is still warm, wet, noisy, complicated biology. It does not operate like a laboratory instrument built to count individual quantum excitations. Even when you're sitting in what feels like complete silence, your auditory system is surrounded by microscopic activity. Molecules in the air are moving because of temperature. Structures inside your ear are moving. Blood is circulating. Cells are active. The nervous system itself produces ongoing electrical activity. A perfectly silent biological detector is therefore not something we possess. This does not mean human hearing is poor. Quite the opposite. Under the right conditions, the ear can detect extraordinarily weak sounds. A healthy human auditory system can respond to pressure variations so small that the movement involved is difficult to imagine on an everyday scale. Yet being extremely sensitive is not the same as detecting individual phonons. Part of the difficulty comes from what a phonon actually is. A phonon is not a universal sound particle travelling through every medium unchanged. It is a quantum excitation belonging to a particular vibrational mode in a particular material system. A phonon inside a crystal is defined by the collective motion of that crystal. A sound wave travelling through air is another mechanical disturbance, but describing one phonon inside a solid and then imagining that exact phonon flying into the air and reaching your ear would be misleading. When vibrational energy passes from a solid into air, the process involves a boundary. The moving surface of the solid pushes on air molecules. That creates a pressure wave. Energy has been transferred, but the microscopic description on one side of the boundary does not have to remain the same on the other side. A phonon inside the solid may contribute to creating excitations in the surrounding medium, but it does not simply keep its identity as though it were a tiny passenger crossing from one material into another. There is another issue. The amount of energy associated with one phonon depends on the frequency of the vibrational mode. A higher frequency vibration has a larger amount of energy per phonon than a lower frequency vibration. This means there is no single universal amount of energy called one phonon. The phrase one phonon tells you the number of vibrational quanta in a particular mode, but you also need to know what kind of mode you're talking about. This matters enormously when we ask whether one quantum of sound could be heard. Human hearing covers a limited range of frequencies, and phonons associated with audible frequencies carry extremely small amounts of energy. In ordinary sound, an enormous number of quantum excitations contribute to the pressure wave that reaches the ear. The smooth sound you experience is a large-scale collective result. Imagine standing on a beach and looking at the sand from far away. The surface appears continuous. You know it is made from individual grains, but the number of grains is so large that removing one would not create any visible difference from where you are standing. Ordinary sound is similar in this respect. The quantum units may be present in the deeper description, but one additional excitation is usually insignificant compared with everything else happening in the wave and in the environment. There is a further complication caused by temperature. At normal temperatures, matter is already full of thermal vibration. atoms and molecules do not wait politely in perfect stillness for an experiment to begin. They are constantly moving because thermal energy is present. Inside a solid, many vibrational modes are naturally populated with phonons simply because the material is warm. Trying to detect one deliberately created phonon under those conditions would be like adding one quiet voice to a crowded room and trying to prove that exactly one new person had spoken. The additional signal would be buried beneath the existing activity. This is why experiments involving individual phonons often begin by cooling the system. Lowering the temperature reduces thermal excitations. If the device is cooled sufficiently, a carefully selected vibrational mode can be brought close to its lowest possible energy state. Once most of the unwanted thermal phonons are removed from that mode, adding one new phonon becomes a much cleaner event. The equipment used for this is very different from the human ear. Researchers may use microscopic or nanoscopic mechanical structures designed to vibrate at very specific frequencies. These devices can be coupled to electrical circuits, optical systems, or other quantum objects. Instead of waiting for a pressure wave to move an eardrum, scientists look for changes in the state of another highly sensitive system. Suppose a tiny mechanical resonator has been cooled near its quantum ground state. The resonator might be designed so that one quantum of mechanical vibration interacts with a superconducting circuit. If the circuit changes in a predictable way when the resonator gains or loses a phonon, the circuit can act as a detector. The phonon does not need to produce a sound that anyone hears. Its existence is inferred from the measurable response of the coupled quantum device. In another type of arrangement, mechanical vibration can interact with light. A small structure may vibrate in a way that changes how light behaves inside a carefully designed optical cavity. If the vibration gains or loses a quantum of energy, the light leaving the system can contain information about that change. By measuring the light very precisely, researchers can learn about the phonon state. This may sound indirect, but indirect measurement is completely normal in physics. You do not need to see something with your eyes for it to be measurable. Many particles and quantum states are detected through the effects they produce on other systems. A phonon can reveal itself by changing the energy, phase, or state of something we know how to measure. There is also a difference between detecting a single phonon and producing a single phonon. Creating exactly one vibrational quantum is itself a difficult task because ordinary methods of making sound tend to produce large, coherent vibrations containing many excitations. If you strike a tuning fork, pluck a string, or play a tone through a speaker, you're not preparing a delicate one-phonon state. You're creating a macroscopic vibration with an enormous amount of energy compared with a single quantum. Quantum experiments must use much more controlled methods. A researcher might begin with another quantum system that can be prepared in a known, excited state. That system can then transfer its energy into the mechanical resonator. If the interaction is designed carefully, one excitation in the first system can become one phonon in the resonator. The procedure resembles passing a single unit of excitation from one place to another. Nothing is literally handed over like a coin, but energy moves between systems in discrete quantum amounts. Once the phonon has been created, researchers can study how long it remains in the resonator, whether it can be transferred somewhere else, and how it interacts with other quantum states. This is where the idea of quantum acoustics becomes much more concrete. We're no longer merely saying that vibrations must be quantized because quantum theory says so. We can build systems where the difference between 0 phonons, 1 phonon, and several phonons matters experimentally. The word acoustic may still give the impression that someone should be able to listen to the experiment. Usually that would not be useful. Many quantum acoustic devices operate at frequencies far above what human ears can hear. The vibrations can also be confined inside tiny structures rather than spreading into the surrounding air as ordinary sound. A phonon can therefore be completely real and experimentally important without ever producing an audible event. There have also been remarkable demonstrations in which mechanical systems are prepared in states that have no straightforward classical equivalent. researchers can place a resonator into quantum superpositions of different vibrational states, couple its motion to quantum bits, and observe interference associated with mechanical excitations. These experiments show that the same quantum rules that govern atoms and light also apply to vibration. That is conceptually important because mechanical objects feel especially classical to us. A vibrating membrane or resonator seems like the sort of thing that should always have a definite amount of motion. We expect it either to be vibrating or not vibrating. Quantum mechanics allows more complicated possibilities when the system is sufficiently isolated and controlled. The challenge is that mechanical devices interact easily with their surroundings. A tiny resonator can exchange energy with the material supporting it. It can be disturbed by thermal motion. It can lose energy through defects. It can couple to stray electromagnetic fields or other vibrations. Every unwanted interaction threatens the delicate quantum state. This is one reason extreme cooling and careful isolation matter so much. Scientists are not making the universe quantum by cooling it. The universe was quantum already. They are reducing the ordinary disturbances that hide quantum behavior. At room temperature, a mechanical system may contain so many thermal excitations that individual phonons become impossible to distinguish. At very low temperatures, the background quiets enough that the discrete structure can emerge. That brings us back to the human ear. Could the ear ever be placed in similar conditions and made sensitive to individual phonons? Practically speaking, the idea runs into immediate problems. A living auditory system must operate at biological temperatures. It depends on complicated molecular processes and contains its own internal noise. Cooling it to the conditions needed for many single phonon experiments would solve the phonon background problem by creating several much larger problems for the listener. Even if we imagine an ideal detector connected somehow to the auditory system, the phrase hearing one phonon would remain ambiguous. Hearing is not simply detecting energy. It is the brain constructing a conscious auditory experience from patterns of neural activity. A quantum detector might register one vibrational excitation, but turning that event into something perceived as a sound would require amplification. Amplification would mean taking the tiny quantum event and using it to trigger a much larger signal. That larger signal could then stimulate the ear or nervous system. At that point, you might hear a click associated with the detection of one phonon, but you would not be directly hearing the phonon itself. You would be hearing an amplified signal produced because the phonon was detected. This is similar to particle detectors used in other areas of physics. A single microscopic interaction can produce a much larger electrical pulse that equipment records. If you connected that pulse to a speaker, you could make every detection produce a click. The clicks would represent particle detections, but the particles themselves would not be making audible noises in the room. Still, there is something appealing about this possibility. A quantum mechanical event can be amplified until it reaches the scale of human perception. The gap between the microscopic and macroscopic world is not absolute. We build instruments precisely because they allow tiny physical events to leave large observable traces. The ear itself already performs amplification. Very weak pressure changes can eventually produce neural signals strong enough to influence perception. The question is whether the original mechanical disturbance is weak enough that individual quantum effects become important before biological noise overwhelms the signal. At ordinary audible frequencies and temperatures, the answer is generally unfavourable. Thermal activity and the enormous number of excitations involved in realistic sounds make the classical wave description overwhelmingly appropriate. The quantum granularity is far below what your hearing system normally reveals. That may sound slightly disappointing. After all, it would be satisfying to discover that sitting in a very quiet room allows you to hear the universe one phonon at a time. But the fact that we cannot do this naturally tells us something important about why the everyday world looks classical. Quantum mechanics does not disappear at large scales. It becomes hidden beneath large numbers of interacting particles, thermal motion, environmental noise, and constant exchanges of energy. The smoothness of ordinary experience emerges because individual quantum steps are tiny compared with the total activity. A glass of water does not look like a collection of separate molecules because there are far too many of them for your eyes to resolve. A beam of ordinary light does not look like individual photons arriving separately because many photons contribute. A sound wave does not usually reveal individual phonons because enormous numbers of vibrational excitations combine into a continuous-looking disturbance. This is one of the most useful lessons phonons give us. The classical and quantum worlds are not separate places. There is no invisible border where physics suddenly changes rules. The same material can be described classically under one set of conditions, and quantum mechanically under another. A large warm mechanical system behaves classically because quantum details are averaged over and disturbed by interactions with the environment. A tiny cold isolated resonator can reveal those details because the unwanted activity has been reduced. The transition is gradual rather than magical. You can think of it as listening to rain. From inside a room, steady rainfall may sound like one continuous wash of noise. Move closer to a window and pay more attention, and individual impacts become easier to distinguish. The rain did not suddenly become discrete when you moved closer. It was made of individual drops all along. Your ability to resolve the individual events changed. Quantum experiments perform something vaguely similar, although with far greater difficulty. They reduce the background, isolate the system, and increase the sensitivity until individual units of excitation can be distinguished. A single phonon can then become a meaningful experimental object. Scientists can ask how long it survives. They can ask whether it can be transferred between devices. They can investigate whether two systems can share quantum correlations involving phonons. They can study whether phonons can carry quantum information. This last possibility is particularly interesting because mechanical vibrations interact with many kinds of physical systems. A vibration can couple to light, electrical circuits, atoms, defects inside solids, and other mechanical structures. That makes phonons possible intermediaries between technologies that otherwise operate in very different ways. Imagine one quantum device that communicates most naturally using microwave signals, and another that works better with optical light. Connecting those two systems is difficult because microwave and optical frequencies are very different. A mechanical resonator can sometimes interact with both, allowing vibrational excitations to help transfer information between them. The phonon becomes something like a translator, although the translation is done through carefully engineered interactions rather than conversation. Energy enters the mechanical mode from one system and can later be transferred into another. Researchers are also interested in using phonons to store information temporarily. The mechanical excitation can persist for some amount of time before losing its energy to the environment. If that lifetime can be made long enough, and the interactions controlled precisely enough, the vibrational mode may function as a kind of quantum memory. None of this requires the phonon to be audible. In fact, the useful quantum devices are often designed specifically to prevent energy from leaking away into uncontrolled sound waves. The better the vibration is confined, the easier it can be to preserve the quantum state. This creates an amusing reversal of ordinary acoustics. In a concert hall, we want sound to reach listeners clearly. In a quantum phonon experiment, researchers may want the vibration to remain trapped inside a microscopic device and avoid communicating with the outside world entirely. A very good quantum resonator can therefore be thought of as a terrible loudspeaker, which in this case is exactly what everyone hoped for. The ability to create and detect individual phonons also allows physicists to test basic ideas about quantum mechanics using mechanical systems. Quantum effects are familiar in atoms and particles because those objects are naturally microscopic. A mechanical resonator is built from enormous numbers of atoms. Seeing it behave quantum mechanically pushes the boundary between what we instinctively call microscopic and macroscopic. The resonator itself may still be tiny by human standards, but compared with an individual atom it can be enormous. If such an object can occupy quantum states, then quantum mechanics is clearly not a special rule limited to elementary particles. It applies to the material as a whole when the right conditions are created. The difficulty is keeping those conditions intact. The larger and more complicated an object becomes, the more ways it can interact with the environment. Each interaction can carry information away from the quantum state. This process helps destroy the delicate relationships needed for clearly observable quantum behavior. Sound and vibration are especially connected to this problem because mechanical systems naturally couple to surrounding matter. A vibration wants to spread. It can leak into supports, substrates, air, and nearby structures. Designing a quantum acoustic device therefore involves controlling where sound is allowed to go. Engineers can shape materials so that certain vibrational frequencies become trapped. They can create structures that reflect phonons. They can build tiny resonators with boundaries designed to reduce energy loss. In effect, they create microscopic acoustic environments that guide quantum sound in particular ways. This begins to resemble something familiar from ordinary acoustics. A room can guide and reflect sound. A musical instrument can confine certain vibrations and reinforce others. A pipe can support particular resonant frequencies. At the quantum scale, similar principles are used with structures small enough and clean enough that individual excitations matter. The same basic physics has been carried into a very different regime. This is why asking whether we can hear one phonon leads to a more interesting answer than a simple yes or no. Human ears are not built to count individual phonons, and ordinary audible sounds involve vast numbers of quantum excitations, but physics can detect individual phonons with specially designed systems. Those phonons can be created deliberately, measured indirectly, transferred between devices, and used as carriers of quantum information. We may not hear them as sounds, but we can observe what they do. There is also a philosophical point hidden in this distinction. Human senses are not the final judges of what counts as physically real. Infrared light is real even though our eyes cannot see it. Ultrasound is real even though our ears cannot hear it. Magnetic fields are real even though we do not have a sense organ that directly reports them. A single phonon does not need to produce a conscious auditory sensation to be part of the physical world. Our instruments extend perception beyond biology. They turn invisible, inaudible, and microscopic processes into signals we can study. Once individual phonons can be created and detected, another question follows almost immediately. If phonons behave like particle-like excitations, how exactly do they travel through a material? Do they move in straight lines? Do they bounce from atoms? What happens when they encounter a defect, a boundary, another phonon, or an electron? Why do some materials carry vibrational energy over long distances while others stop it quickly? Those questions take us away from the problem of detecting one quantum and into the interior of matter itself, where quantum sound does not simply exist but moves, scatters, transfers energy, and helps determine how the material behaves. Once we begin treating vibration in quantum terms, another question becomes unavoidable. If a phonon is a quantum excitation of a material, what does it actually mean for that excitation to move from one place to another? At the classical level, we already have a comfortable picture. One region of matter moves, neighbouring regions respond, and a wave travels through the material. At the quantum level, the same physical system is still there, but we describe its energy differently. Instead of imagining only a smooth continuous vibration, we can also describe the collective motion in terms of phonons, and then ask how those phonons propagate through the structure, what slows them down, what redirects them, and what eventually happens to their energy. It helps to return for a moment to a simple crystal. Imagine a large regular arrangement of atoms, each one sitting near a preferred position and interacting with the atoms around it. None of them is perfectly still, but the overall structure is stable. If some energy is added to one region, the atoms there begin participating more strongly in certain vibrational motions. Those motions affect their neighbours, and the disturbance can spread through the crystal. In a classical description, we would say that a vibrational wave is moving through the solid. In the quantum description, we can talk about phonons carrying vibrational energy through the material. Both descriptions refer to the same underlying system, but they emphasize different features. This is important because a phonon does not move by jumping from atom to atom, like a person crossing stepping stones. The atoms are not tiny stations waiting for a phonon to arrive, stay briefly, and then depart. The excitation belongs to the collective pattern of motion. As that pattern changes across the material, the energy associated with it can propagate. A better mental picture is a coordinated disturbance spreading through a crowd. If people are standing close together and one person moves, the response can travel through the group. No single individual carries the entire disturbance from beginning to end. The movement exists through the relationships between many participants. A phonon has that same collective character, although quantum mechanics gives the excitation properties that allow physicists to treat it in many calculations as if it were a particle moving through the material. How easily that motion occurs depends enormously on the material itself. A perfectly ordered crystal provides a very regular environment. The atoms repeat in predictable patterns, which means certain vibrational modes can travel efficiently. A real material, however, is never perfectly simple. There may be missing atoms, foreign atoms, boundaries between different crystal regions, changes in composition, rough surfaces, and many other imperfections. Every one of these can affect the movement of phonons. This is where scattering becomes important. When a phonon encounters something that disrupts the regular structure, its directional state may change. Some of its energy may be redirected into another vibrational mode. Several phonons may interact. A phonon may transfer energy to an electron. The original neat path becomes more complicated. The word scattering may make you imagine billiard balls bouncing from one another, and sometimes that picture is useful as a rough starting point. The actual quantum process is not a collection of little hard spheres colliding inside the solid. The phonons are collective excitations, so scattering means that one pattern of vibration is being transformed through its interaction with another part of the system. If a material is extremely clean and well ordered, certain phonons can travel relatively long distances before being scattered. If the material is disordered, they may be redirected much more frequently. That difference influences how quickly vibrational energy spreads. One place where this becomes easy to appreciate is heat conduction. Suppose one side of a solid object is warmer than the other. The warmer region contains more energetic microscopic motion. Vibrational energy begins moving toward the cooler region. In many solids, phonons are major carriers of that energy. If phonons can move through the material with relatively little scattering, heat can travel efficiently. If they are constantly scattered, heat moves less effectively. This means that the ability of a material to conduct heat is deeply connected to the way quantum vibrations travel inside it. Diamond provides a striking example. People usually think of diamond in terms of hardness, jewellery, or the impressive ability of a tiny transparent object to become extremely expensive after someone places it in a velvet box. From the viewpoint of phonon physics, diamond is also remarkable because its strong atomic bonds and ordered structure allow vibrational energy to move very efficiently. Other materials behave very differently. In something structurally complicated or disordered, phonons may encounter frequent interruptions. Heat then spreads more slowly. This is one reason materials with very different appearances can also have very different thermal properties. The connection between phonons and heat also explains why temperature changes the way phonons move. At higher temperatures, many more vibrational excitations are present. The material becomes a busier place at the microscopic level. Phonons have more opportunities to interact with other phonons, and these interactions can make their paths less straightforward. One phonon may scatter from another. Their energies and directions may be redistributed among new vibrational excitations. Nothing has been lost from nature, but the organized movement of energy becomes less simple. If you imagine trying to walk across an empty room, movement is easy. Now imagine the same room filled with people wandering in every direction. You can still cross it, but you're much more likely to be redirected, slowed, or forced to take a complicated route. A warm crystal is not literally crowded with little phonon people, but the analogy captures why increasing vibrational activity can lead to more scattering. Boundaries create another interesting problem. Eventually, a phonon moving through a material may reach a surface or an interface where one material meets another. What happens then depends on how well the vibrational properties of the two materials match. Part of the vibrational energy may pass across the boundary, part may be reflected. Some may be converted into different kinds of vibrational motion. The details depend on the atomic structures and on the frequencies involved. This is the microscopic version of something familiar from ordinary sound. If you speak in a room, sound waves reaching a wall are not simply erased. Some of the sound reflects back into the room, some energy enters the wall, some is absorbed and eventually becomes less organized microscopic motion. At the quantum level, the transfer of vibrational energy across boundaries can be described in terms of phonons interacting with the available modes on either side. If the second material does not easily support the same kind of vibration, transmission may be poor. More energy may be reflected or redistributed. This becomes extremely important in very small devices. In modern electronics, heat often has to travel across interfaces between different materials. A computer chip, for example, may contain many layers and structures made from different substances. If phonons have difficulty crossing those boundaries, heat can build up even when the individual materials conduct heat reasonably well on their own. Engineers therefore care about something called thermal boundary resistance, although the name is less important here than the idea. A boundary can become a bottleneck for vibrational energy. Heat approaches the interface through phonons, but the available vibrational states on the other side may not provide an easy continuation. It's almost like arriving at a railway station where the tracks suddenly change width. The journey can continue, but transferring from one system to another becomes less efficient. Phonons also interact strongly with imperfections. A crystal may contain an atom of the wrong type sitting where another atom would normally be. It may contain a vacancy where an atom is missing. It may contain a dislocation, which is a defect in the orderly arrangement of the crystal. To us, these irregularities are unimaginably small. To a vibrational excitation travelling through the material, they can matter greatly. Different phonons respond differently depending on their frequency and wavelength. A long wavelength vibration may pass around a very small imperfection with relatively little disturbance. A shorter wavelength vibration may be scattered much more strongly. This means that the microscopic structure of a material can influence different parts of its vibrational spectrum in different ways. Scientists can deliberately use this fact. By designing materials with carefully chosen structures, they can encourage some phonons to travel while blocking others. They can create tiny repeated patterns that act somewhat like filters for vibration. This leads to structures often described as phononic materials or phononic crystals. The name is chosen deliberately because there is a useful comparison with the way specially structured materials can control light. By arranging a material on the right scale, engineers can create ranges of vibration that are difficult or impossible to propagate through the structure. In other words, they can build something that behaves like a barrier for certain kinds of sound. This does not necessarily mean audible sound. The frequencies involved can be far beyond human hearing. What matters is that the underlying mechanical vibration is being controlled. Such structures can trap vibrational energy in particular regions. They can guide it along specific paths, they can reflect selected frequencies, they can keep unwanted vibration away from sensitive parts of a device. At the classical level, this resembles the engineering of acoustic filters and resonators. At the quantum level, the same ideas can be used to control individual or small numbers of phonon excitations. Guiding phonons is especially interesting for quantum technology. If a phonon can carry quantum information, it becomes useful to have something like a microscopic pathway that determines where the excitation is allowed to go. Researchers can create tiny channels in which mechanical waves are confined, much as an optical fibre guides light. The details are different because the phonon depends on the material, but the general goal is similar. Keep the excitation from spreading randomly and direct it toward another part of the device. The challenge is that phonons have many ways to lose their useful organization. A vibrational excitation can scatter into other modes. It can leak into the surrounding material. It can interact with thermal phonons. It can transfer energy to electrons or defects. Every one of these processes can reduce the lifetime of a carefully prepared quantum state. For everyday sound, none of this seems particularly troublesome. If you strike a bell, you expect the sound to fade. The vibration gradually loses energy to the surrounding air, the support holding the bell, internal friction, and other forms of motion. Eventually the organized ringing is gone and its energy has become dispersed. For quantum acoustics, however, that fading is a serious problem. If a single phonon is being used to store or carry quantum information, researchers want to know exactly where the energy goes and how quickly the state loses its coherence. Coherence is one of those quantum words that can sound much more intimidating than the basic idea. A carefully prepared quantum state contains precise relationships that allow quantum effects such as interference to occur. Interactions with the surrounding environment can disturb those relationships. A phonon that interacts unpredictably with a large warm material may quickly lose the delicate quantum properties researchers wanted to preserve. The vibrational energy may still exist somewhere, but the original quantum information can become effectively inaccessible. This is why quantum phonon experiments are often built around isolation. Researchers cool devices, reduce defects, carefully engineer supports, and design structures that prevent vibration from escaping. Some devices are suspended by extremely small connections so that mechanical energy has fewer routes into the surrounding material. Others use repeated structures that reflect phonons back toward the central resonator. The device becomes a kind of microscopic vibration trap. There is something slightly amusing about the engineering goal. If you were building a musical instrument, you might want the vibration to couple efficiently to the surrounding air so that people can hear it. If you're building a quantum mechanical resonator, you may want exactly the opposite. You want the vibration to remain inside the device and refuse to share its energy with anything nearby. A successful quantum resonator can therefore be wonderfully bad at entertaining an audience. The movement of phonons also depends on whether we are dealing with a single isolated excitation or a large population of them. With many phonons present, interactions between vibrations become increasingly important. At high enough energies, the simple picture of independent phonons travelling through the crystal becomes less accurate because the vibrations influence one another strongly. At low temperatures, some materials offer a cleaner environment. Fewer thermal phonons are present, so individual excitations can travel with less disturbance. This is one reason cooling is so useful when studying quantum sound. Cooling does not merely make things quiet in the everyday sense. It reduces the microscopic population of unwanted vibrational excitations that would otherwise interfere with the experiment. There is also a close connection between the speed of sound in a material and the way certain phonons propagate. Long-wavelength acoustic phonons correspond closely to the familiar elastic waves described by classical acoustics. Their collective motion can travel through the material at speeds related to the material's stiffness and density. The quantum description does not throw away those classical properties. It builds on them. This is a recurring feature of quantum physics. When large numbers of phonons occupy a mode in an organized way, the result can closely resemble a classical sound wave. The quantum and classical pictures join smoothly rather than fighting for ownership of the phenomenon. A classical pulse travelling through a solid can therefore be thought of as a large-scale collective state involving many phonon excitations. If the vibration is strong enough and the system large enough, tracking individual quanta would be unnecessary. The wave description tells us everything useful. Reduce the energy enough, cool the system enough, and isolate one particular mode, and suddenly the number of phonons becomes important. The same material can therefore support behaviour that looks entirely classical in one experiment and clearly quantum in another. Electrons add another layer to the movement of quantum sound. In conducting materials, electrons can interact with lattice vibrations as they move. An electron may release some of its energy by creating a phonon. It may absorb a phonon and gain energy. Its direction may change after interacting with a vibration. This exchange helps explain why the electrical resistance of many metals depends on temperature. As the material warms, more lattice vibrations become available, and electrons have more opportunities to be scattered. From the electron's point of view, a warm lattice is a less peaceful environment to travel through. The same interaction between electrons and phonons can produce much more surprising behaviour under the right conditions. In conventional superconductors, phonons help create an effective connection between electrons that allows them to form correlated pairs. Once a large number of those pairs enter the superconducting state, electrical current can move without ordinary resistance. The details belong to a larger story about superconductivity, but for our purposes it is enough to notice how deeply vibrational motion is woven into the behaviour of matter. The quantum version of sound is not sitting quietly in one corner of physics. It is involved in heat, electricity, material properties, and collective quantum effects. Phonons can interact with light as well. When light enters certain materials, it can exchange energy with vibrational modes. A photon may lose some energy while creating a phonon, or gain energy by absorbing vibrational energy already present. These interactions allow scientists to study material vibrations by examining how light changes after passing through or scattering from the material. This is useful because light can act as a messenger between a microscopic vibration and our measuring equipment. We may not be able to place a tiny microphone beside an atomic lattice, but we can shine carefully controlled light on the material and examine what comes back. Changes in the light reveal information about the vibrational excitations inside. Modern quantum devices can use this interaction in an even more controlled way. A mechanical resonator may be coupled to an optical cavity so that very small changes in vibration alter the behaviour of trapped light. Measuring that light allows researchers to infer what the mechanical system is doing. The phonon moves or changes, the optical signal responds, and information about quantum sound becomes accessible without anyone needing to hear anything. Microwave signals can play a similar role in other devices. Superconducting circuits often operate naturally at microwave frequencies, and mechanical resonators can be designed to exchange excitations with them. A quantum excitation can begin in an electrical circuit, enter a mechanical mode as a phonon, remain there briefly, and later be transferred again. That process is one reason phonons are being explored as possible links between different quantum systems. A mechanical vibration can interact with objects that do not otherwise communicate easily. The idea becomes even more interesting when phonons are confined to extremely small structures. In a large solid, vibrational energy can spread in many directions and occupy many possible modes. In a carefully engineered nanoscale device, the options can be drastically reduced. The phonon may be restricted to a narrow path or a small resonator. Researchers can then control its environment with much greater precision. It is similar to the difference between releasing a ball into an open field and placing it inside a narrow track. The second situation gives far more control over where it can go. Quantum mechanics adds its own complications, of course. A phonon travelling through a carefully designed system can show wave-like behaviour. Different possible paths can interfere. A vibrational excitation can be shared between different regions in ways that do not resemble a classical object choosing one definite route. The particle language remains useful, but the wave character never truly disappears. This is exactly what we should expect. A phonon begins as the quantum description of a wave. It would be rather surprising if it behaved like a classical pebble, simply because we decided to give it a particle-like name. Under suitable conditions, phonon states can be placed into quantum superpositions. A mechanical system can be prepared so that its vibrational state cannot be described as simply having one definite classical motion. Experiments of this kind are difficult because vibrations couple so readily to the environment, but they demonstrate something important. Mechanical motion itself can participate fully in quantum behavior. The atoms making up the resonator may number far beyond anything we could track individually, yet their collective motion can still obey quantum rules. The question of how quantum sound moves through matter therefore has several answers depending on what scale we choose to describe. At the atomic level, neighbouring particles interact and transmit mechanical disturbance. At the classical level, waves propagate through the material. At the quantum level, the allowed vibrational modes have discrete excitations, and those phonons can carry energy, scatter, reflect, interact, and be converted into other excitations. None of these pictures cancels the others, they fit together. The smooth pressure wave you hear through a wall and the phonons scattering from a defect inside that wall are different levels of the same broad physics of vibration. Once scientists learned not only to describe these excitations, but to guide, trap, create and measure them with increasing precision, sound entered a rather unusual new territory. Mechanical vibrations could be prepared in quantum states, exchanged with quantum bits, coupled to individual atoms, and used in experiments where a single phonon matters. That takes us beyond simply asking how sound moves through matter, and into the much stranger question of what happens when sound itself becomes a deliberately controlled quantum system. Once scientists learned how to create, guide and detect very small numbers of phonons, sound stopped being only a subject for concert halls, speakers, musical instruments, and ordinary materials. It became something that could be placed directly inside quantum experiments. A vibration could be cooled close to its lowest possible energy, coupled to a quantum bit, exchanged with light, stored for a short time, and manipulated in ways that have no ordinary acoustic equivalent. This area is known as quantum acoustics, and despite the familiar word acoustics, it usually has very little to do with sounds that a human being could actually hear. The vibrations are often far too high in frequency, far too weak or far too tightly confined inside microscopic structures to produce anything resembling an audible tone. What makes them acoustic is that they are mechanical vibrations of matter. What makes them quantum is that individual units of those vibrations matter. The basic goal is easier to understand if we imagine an ordinary musical instrument and then make almost everything about it smaller and more controlled. A guitar string can vibrate in many different ways, and once it is plucked, it contains an enormous amount of vibrational activity compared with a single quantum. It is warm, exposed to the environment, connected to the body of the guitar, surrounded by air, and constantly losing energy. None of that is helpful if you want to prepare one precise quantum state and preserve it long enough to study. Quantum acoustics therefore replaces the guitar string with carefully engineered resonators that may be microscopic or even smaller. These structures are designed to vibrate at specific frequencies while interacting as little as possible with everything around them. The first challenge is getting the unwanted vibration out of the system. At ordinary temperatures, thermal energy fills materials with phonons. Even when a device looks perfectly still, its atoms are moving and its vibrational modes are populated. If you want to know whether you have deliberately added one phonon, that background activity is a serious problem. Researchers cool their devices to extremely low temperatures so that many of the thermal excitations disappear. The goal is to bring a selected mechanical mode close to its lowest possible quantum state. Once that happens, the difference between no added phonons and one added phonon can become meaningful. A vibration that would be completely buried at room temperature can now stand out from the much quieter background. This is one of the recurring themes in experimental quantum physics. The strange behavior was not created by cooling the system. Quantum rules were always there. Cooling simply removes enough ordinary thermal activity that the quantum structure becomes easier to see. Even at the lowest possible state, the mechanical system is not perfectly motionless. Quantum mechanics leaves it with zero-point motion, the unavoidable residual motion of the ground state. This is not ordinary shaking caused by heat. It remains even when the system has been cooled as far as the quantum description allows. A quantum resonator therefore never becomes the completely frozen object that classical intuition might expect. Researchers can then begin adding excitations deliberately. One method is to couple the mechanical resonator to another quantum system whose state can be controlled more easily. A superconducting quantum bit, for example, can be prepared with 1 unit of excitation. Under the right conditions, that excitation can be transferred into the mechanical resonator. The quantum bit loses its excitation, and the resonator gains 1 phonon. The process is not like dropping a tiny object into a container. Nothing resembling a grain of sound falls from the electrical circuit into the mechanical device. What is transferred is a quantum of energy and the information associated with the quantum state. The electrical system and the mechanical system are designed so that they can exchange that excitation in a controlled way. This ability to move quantum states between different physical systems is one reason phonons are so interesting. Quantum technologies are built from many kinds of hardware. Some systems use superconducting electrical circuits, others use atoms, ions, defects inside crystals, or particles of light. These systems can be excellent at different tasks, but they do not always communicate easily with one another. Their natural frequencies and physical interactions may be very different. Mechanical vibration can sometimes provide a bridge. A carefully designed resonator may interact with an electrical circuit on one side and light on the other. Quantum information can then be transferred through the mechanical system. The phonon becomes an intermediary between technologies that otherwise speak very different physical languages. You can think of it as a translator in a meeting where everyone understands physics, but nobody has agreed on the same communication method. One system prefers microwave signals, another prefers optical light, and the mechanical resonator sits between them, helping energy move from one form to another. It is a very small meeting, admittedly, and nobody has provided biscuits, but the general problem is familiar. The interaction between phonons and light is especially important in a field known as optomechanics. In these systems, a mechanical structure is arranged so that its motion affects light trapped or guided nearby. A very small displacement can change how light behaves inside the device. The light can then be measured to reveal information about the mechanical vibration. The interaction can also work in the opposite direction. Light can push on matter. The forces involved are usually extremely small, but in microscopic devices they can be significant enough to influence mechanical motion. Researchers can therefore use light not only to measure vibrations but also to cool, excite, and control them. This creates a remarkably intimate connection between photons and phonons. A photon can enter a device, interact with a mechanical mode, and leave with slightly different energy because a phonon has been created or absorbed. By examining the light, scientists can infer what happened to the vibration. Nothing about this requires the vibration to become audible. The entire exchange can occur inside a structure far smaller than anything associated with ordinary sound equipment. Yet the mechanical physics underneath it is related to the same basic idea as a speaker pushing air or a string vibrating on an instrument. Matter moves, energy is transferred, and the motion can be organized into modes. Quantum acoustics becomes stranger when researchers prepare phonons in states that do not resemble ordinary classical vibration. A classical resonator can have a definite amplitude and phase. It moves back and forth in a predictable way. A quantum resonator can instead occupy states where the vibration cannot be described by one simple classical motion. One possibility is a state with a definite number of phonons. If a resonator contains exactly 1 phonon in a particular mode, that state does not behave like a tiny version of an ordinary vibrating string. It has properties that belong specifically to quantum mechanics. Scientists can also create superpositions involving different vibrational states. The mechanical system may be prepared in a quantum condition that combines possibilities which, in classical language, would seem mutually exclusive. The resonator is not simply vibrating with one definite amount of energy in the ordinary sense. Its state contains a quantum relationship between different possibilities. This is important because mechanical motion feels so familiar and physical. We expect quantum strangeness from electrons and photons because we are accustomed to being told that microscopic particles behave strangely. A vibrating object seems more ordinary. It is made from a large number of atoms. It has mass. It occupies a visible or at least measurable piece of material. Yet quantum theory makes no special exception for objects simply because they contain many atoms. If the motion is isolated carefully enough and the environment is controlled, the collective vibration of a mechanical object can display quantum behavior. The difficulty grows rapidly as the object becomes larger. Larger systems interact with more of their surroundings. They exchange heat, vibrational energy, electromagnetic energy, and information with the environment. Those interactions make delicate quantum states difficult to preserve. The problem is often described in terms of decoherence. A quantum superposition depends on precise relationships between the different parts of the state. When the system interacts uncontrollably with its surroundings, information about those relationships leaks into the environment. The superposition becomes harder to observe as a coherent quantum state. Mechanical devices are particularly vulnerable because vibration naturally wants to spread. If a resonator is attached to a support, energy can leak through that support. If it touches another material, phonons can escape into it. If it is surrounded by gas, motion can couple to the gas. Internal defects can scatter vibrations. Thermal phonons can collide with a carefully prepared excitation. Building a quantum acoustic device is therefore partly an exercise in persuading vibration to stay exactly where it is supposed to stay. Engineers can do this by shaping the material itself. Repeating microscopic structures can be designed so that certain vibrational frequencies cannot propagate through them easily. A resonator can then be surrounded by structures that act like mirrors for phonons. The desired vibration becomes trapped in a central region because the surrounding material refuses to carry that frequency away efficiently. The idea resembles soundproofing, but at a much smaller and more precise scale. Instead of placing thick material on a wall to reduce noise, researchers design the internal structure of a device so that particular vibrational modes are blocked. These structures are sometimes called phononic crystals. Their repeating patterns affect mechanical waves in ways that can be engineered very carefully. Some frequencies are allowed to propagate, while others encounter ranges where propagation is strongly suppressed. A phononic crystal can therefore guide vibration, reflect it, or confine it. This opens the possibility of building components for sound that resemble components already used with light and electricity. A pathway can guide phonons from one location to another. A cavity can trap them. A filter can favor certain frequencies. A coupling region can allow two resonators to exchange excitations. A network of such devices can begin to look like a tiny acoustic circuit. In ordinary electronics, circuits guide electrical signals. In photonics, structures guide light. Quantum acoustics explores ways of guiding mechanical excitations with similar precision. There are some advantages to using phonons. Sound travels much more slowly through materials than light travels through vacuum. That may initially sound like a disadvantage, especially if you have ever been frustrated by anything that operates slowly. In quantum devices, however, slower propagation can be useful. A phonon with a particular frequency can have a much shorter wavelength than a photon of the same frequency. This means acoustic components operating at certain frequencies can be made very compact. Long interactions can be fitted into small physical spaces. The slower speed also means a signal can spend more time inside a small device. This can strengthen interactions between the phonon and other quantum systems. A quantum bit may have more opportunity to exchange energy with the mechanical excitation before it escapes. This is one reason researchers are interested in surface acoustic waves. These are mechanical waves that travel mainly along the surface of a solid, rather than through its entire volume. They are already used in conventional technology for filtering and processing signals, especially in communication devices. At the quantum level, similar surface waves can be cooled and coupled to quantum circuits. A superconducting quantum bit can emit or absorb individual acoustic excitations travelling along a surface. In effect, the device can communicate using quantum sound. Again, nothing audible needs to occur. The frequency may be far outside human hearing, and the vibration may be confined to a microscopic region. The word sound here refers to mechanical wave motion, not to a conscious experience inside an ear. The ability to send individual phonons along a controlled path raises an obvious possibility. Could phonons carry quantum information between different parts of a processor? In principle, yes. If a phonon is prepared in a state that depends on a quantum bit, and if that state can travel without being destroyed by the environment, another part of the device may receive the information. The challenge is keeping the excitation coherent during the journey. Every defect, thermal vibration, and unwanted interaction provides an opportunity for information to leak away. Engineers therefore need extremely clean materials, carefully chosen frequencies, very low temperatures, and structures designed to prevent scattering. Phonons may also be used as temporary quantum memories. If an electrical or optical quantum state can be transferred into a long-lived mechanical mode, the information can be stored there and retrieved later. The storage time does not need to be enormous to be useful. Even a short delay can help synchronize different operations inside a quantum system. This is similar to placing information on hold while another part of the device catches up. The phonon waits in the mechanical resonator until the next step is ready. Quantum acoustics also allows experiments in which one artificial atom interacts with sound. A superconducting quantum bit can behave in some ways like an atom with controllable quantum energy states. Couple it strongly enough to an acoustic pathway, and the artificial atom can emit a phonon into the material, then later absorb another. The resemblance to an ordinary atom interacting with light is striking. In quantum optics, atoms emit and absorb photons. In quantum acoustics, engineered quantum systems can emit and absorb phonons. The difference in the speed of sound produces some unusual possibilities. Light moves so quickly that a photon generally leaves a small laboratory system almost immediately. An acoustic excitation moves much more slowly. Under carefully designed conditions, a phonon, emitted by a quantum bit, can travel through a device, reflect from a boundary, and return while the quantum bit is still evolving. The emitter can then interact with its own earlier emission. That sounds almost like science fiction, but it follows from the simple fact that mechanical waves take time to move through matter. Researchers can use delay lines to create controlled situations where the history of a system feeds back into its later behavior. Instead of the environment simply carrying information away forever, some of it can return. This gives physicists ways to study quantum systems with memory. The future behavior of the quantum bit depends not only on its present state, but also on an excitation it emitted earlier and later encountered again. At the everyday scale, echoes are familiar. You shout toward a distant wall, and your own voice returns after a delay. Quantum acoustics can create something loosely comparable on a microscopic scale, except the returning excitation may contain only one phonon and can interact coherently with the quantum system that produced it. One could call it a quantum echo, although it would be an extremely disappointing echo if your goal were to hear your own voice. The strange behavior continues when several phonons interact. In a perfectly simple model, phonons might pass through one another without much effect. Real materials are not perfectly simple, atomic interactions are not completely linear, and phonons can scatter from other phonons. Two excitations can combine their energy into another vibrational state, or one can produce others under allowed conditions. These processes influence heat flow and determine how long particular phonon states survive. For quantum technology, such interactions can either be a problem or an opportunity. Uncontrolled scattering destroys carefully prepared states. Controlled interactions, however, could allow phonons to influence one another in useful ways. Researchers would like to build mechanical systems where one phonon can significantly affect the behavior of another. That is difficult because individual phonons normally interact weakly. Various engineered devices attempt to strengthen these interactions by coupling the mechanical motion to quantum circuits, atoms, or optical fields. If the interaction becomes strong enough, a mechanical device could perform operations on quantum information rather than merely carrying it. Another unusual direction involves entanglement. Two quantum systems can be prepared so that their states are correlated in a way that cannot be explained by assigning each one an independent classical condition. Phonons can participate in such states. A mechanical resonator may become entangled with a photon, a quantum bit, or another mechanical resonator. Measuring one part of the combined system then reveals correlations with the other. This matters because entanglement is one of the central resources in quantum information science. Showing that mechanical vibrations can share entanglement demonstrates that phonons are not merely a useful bookkeeping trick for heat and sound. Their quantum states can carry the same kinds of non-classical relationships found throughout quantum physics. There is something remarkable about imagining two pieces of material connected through a quantum relationship involving their motion. The objects need not visibly shake. The displacement may be extraordinarily small, yet their vibrational states can still share information that has no ordinary classical explanation. Mechanical systems are also being explored as tools for detecting extremely weak forces. A resonator near its quantum ground state can respond to tiny disturbances. If researchers understand its quantum noise well enough, they can use it as a sensitive probe. Such devices may eventually contribute to measurements of forces, fields, masses, or other physical effects that are difficult to detect by conventional methods. This brings quantum acoustics into contact with precision measurement. The same effort used to isolate a single phonon can produce instruments capable of responding to extraordinarily small changes in their environment. There is an interesting tension here. For quantum information, researchers often want the mechanical system to ignore the outside world completely. For sensing, they want it to respond to one particular outside influence while ignoring everything else. The art of designing the device lies in deciding which interactions are welcome and which should be suppressed. That distinction appears throughout physics. A good sensor must be sensitive, but only to the thing you want to measure. If it responds equally to temperature changes, vibrations from the building, electrical noise, and someone closing a door down the corridor, the experiment becomes much less enjoyable. Quantum acoustic systems therefore sit in carefully controlled environments, where even tiny disturbances can matter. The field also reminds us how much the meaning of sound depends on scale. At the human level, sound means voices, music, noise, and pressure, waves arriving at the ear. At the microscopic level, the same broad physics becomes a study of quantized mechanical excitations. The ordinary experience of hearing is only one small part of the physical world of vibration. A phonon can exist at a frequency no ear could detect, inside a device no eye could see directly, at a temperature where ordinary biological hearing would be the least of anyone's concerns. It can carry quantum information, become entangled, interact with light, influence a superconducting circuit, and disappear into another vibrational mode without ever producing anything we would call a sound in daily life. Yet the connection to ordinary acoustics remains. A mechanical medium moves. The motion has organized modes. Energy travels through those modes. Boundaries reflect it. Structures confine it. Resonance strengthens particular patterns. The same basic ideas that explain why a guitar string rings or why a room echoes remain present. But quantum mechanics changes what we can say about the smallest excitations. That is perhaps the strangest thing about quantum acoustics. It does not require us to abandon everything familiar about sound. Instead, it takes familiar ideas and pushes them into conditions where their hidden quantum structure becomes visible. A resonator is still a resonator. A wave is still a wave. A reflection is still a reflection. A vibration can still travel, interfere, and lose energy. What changes is our ability to ask about individual quanta. How many excitations are present? Can we prepare exactly one? Can we keep it isolated? Can we transfer it to another device? Can two phonons interfere? Can a vibrational state become entangled with light? Can mechanical motion store quantum information? Questions that would be meaningless for a ringing bell become practical questions in a laboratory. And after following sound this far, from pressure waves in air to individual excitations in tiny quantum devices, we arrive at a deeper problem. We have repeatedly called phonons particles, waves, excitations, and collective patterns, depending on what we were trying to explain. Each description works, but none feels quite like the simple answer we might have expected when we first asked what sound is made of. That leaves one final question waiting underneath everything we have discussed so far. If a phonon is not a fundamental particle, if sound cannot exist without a medium, and if the same vibration can be described as both a wave and a collection of quantum excitations, then perhaps asking what sound is made of is not really a question about finding one smaller object inside it. Perhaps it is a question about what it means for a physical pattern to exist at all. After following sound from vibrating objects to pressure waves, from atomic motion to phonons, and from ordinary materials into quantum acoustic devices, we can finally return to the question that started the whole discussion. What is sound actually made of? It is tempting to give a simple answer and say that sound is made of particles called phonons. That answer is useful in some situations, but it is not quite complete. A phonon is not a fundamental ingredient of nature in the same way that an electron is. Sound is not built from a collection of tiny phonon objects that exist independently and happen to gather together whenever someone speaks or a guitar string is plucked. The more accurate answer depends on which level of the physical process we're describing. At the everyday scale, sound is a mechanical disturbance travelling through matter. If someone speaks across a room, their vocal cords create vibrations. Those vibrations produce changing pressure in the surrounding air, and the changing pressure spreads outward. Molecules move over small distances, past the disturbance to neighbouring molecules, and eventually cause motion in your eardrum. Nothing in that description requires us to talk about individual phonons. Classical physics describes the process extremely well because the number of microscopic excitations involved is so large that the sound behaves like a smooth wave. If we move inside a solid and examine its vibrations at much smaller scales, quantum mechanics becomes important. The atoms are arranged in a structure and interact with one another. They can participate in collective vibrational modes, and the energy associated with those modes comes in discrete quantum amounts. One quantum of excitation in such a mode is called a phonon. In that setting, saying that vibrational energy is carried by phonons is both useful and physically meaningful. The important detail is that the phonon belongs to the vibration. It is not a separate piece of matter hidden underneath the vibration. You cannot remove all the atoms from a crystal and leave the phonons behind. Without the material, there are no lattice vibrations to quantize, and therefore no phonons belonging to that lattice. The existence of the phonon depends on the organized behavior of the underlying matter. This makes phonons a good example of emergence. Emergence occurs when a collection of smaller components behaves in a way that is best described using a new concept that does not belong to any one component by itself. Temperature is a familiar example. A single molecule does not have the temperature of a room. Temperature describes the statistical behavior of enormous numbers of particles. Pressure works in a similar way. One molecule colliding with a wall is not the pressure of the entire gas. Pressure becomes useful when many collisions are considered together. A phonon follows the same broad idea. No single atom contains the phonon. Many atoms participate in a coordinated vibrational pattern, and quantum physics allows that pattern to be described in terms of discrete excitations. The phonon belongs to the collective behavior. This may seem like a small distinction, but it changes the way we should answer the question of what sound is made of. If you ask what a wooden table is made of, eventually you can point to atoms as constituents. Remove enough atoms and there is less table. If you ask what sound is made of, there is no equivalent collection of permanent sound particles waiting inside the material. Sound is an activity of matter. It exists because matter is moving in an organized way. A wave provides an ordinary example of the same principle. Consider a wave moving across the surface of water. The wave is physically real. It carries energy. It can move across a large distance. It can reflect from a boundary and interfere with another wave. Yet the wave is not an additional substance placed on top of the water. It is a pattern in the motion of the water. You could replace many of the water molecules and still produce the same kind of wave. The identity of the individual molecules is not what defines the wave. What matters is how the system is moving. Sound works similarly. The air molecules between a speaker and your ear are not individually important to the identity of a musical note. The molecules can be replaced by other molecules, and the same pressure pattern can still travel. The information is contained in the organized changes of pressure and motion. This is why one sound can pass through several completely different physical systems while remaining recognizable. Imagine someone speaking into a microphone. Their voice begins as mechanical vibration in the vocal system. It becomes a pressure wave in air. The microphone converts that motion into an electrical signal. The signal may be converted into digital information and stored. Later, a speaker turns electrical activity back into mechanical motion. The speaker creates another pressure wave, and your ear converts that into neural activity. The material carrying the pattern changes several times, but you can still recognize the same voice. There was never one physical substance called the voice traveling through every stage. What survived was organized information encoded in different physical systems. Sound therefore belongs to a larger class of physical phenomena in which patterns matter as much as objects. Physics often begins by teaching us to identify things. Particles, atoms, planets, fields, and forces sound like individual items that can be named separately. Once we study complicated systems, however, we discover that relationships and collective behavior can be just as important. A phonon is useful precisely because tracking every individual atom would often hide the behavior we actually care about. Suppose a vibrational excitation is moving through a crystal containing an enormous number of atoms. We could attempt to describe the motion of every atom separately. Quantum mechanics allows such a description in principle, but it would be unnecessarily complicated for many problems. Instead, we identify the collective vibrational modes and describe their excitations as phonons. Suddenly, questions about heat flow, scattering, electrical resistance, and mechanical vibration become much easier to organize. The phonon is therefore not an approximation invented because physicists were tired of tracking atoms. It reflects a genuine structure in how the material behaves. Experiments can create individual phonon excitations. They can measure how phonons interact. They can transfer them between devices. They can observe their effects on electrons, light, and quantum circuits. The fact that a phonon emerges from collective behavior does not make it less real. It simply tells us what kind of physical object it is. This raises a useful question about the word particle itself. In everyday life, a particle sounds like a tiny solid object. A grain of sand is a particle. A speck of dust is a particle. If that everyday picture is carried directly into quantum physics, confusion arrives very quickly. Quantum particles do not behave like miniature billiard balls. Electrons display wave behavior. Photons interfere. Quantum states can extend across space. The distinction between wave and particle is not as simple as choosing which picture is correct. A phonon makes this especially obvious because it begins as a quantum description of a wave like collective motion. Calling it a particle does not erase the wave. The particle language tells us that the vibrational excitation comes in discrete units and can exchange energy in particle-like ways. The wave language tells us how the collective disturbance is distributed and propagates. Both descriptions are useful because quantum objects do not have to fit into the categories our everyday experience gives us. This is why asking whether sound is really a wave or really made of particles gives us a slightly misleading choice. At the classical scale, sound behaves as a wave in matter. At the quantum scale, the vibrational modes of matter have discrete excitations that we call phonons. One description does not need to defeat the other. The scale and the experiment determine which description is useful. If you are designing a recording studio, you care about waves reflecting from walls, being absorbed by materials, and forming resonances in the room. Counting phonons would add tremendous difficulty without improving the design. If you are cooling a microscopic mechanical resonator and attempting to store a single quantum excitation, the classical wave description alone may no longer be sufficient. Then the number of phonons becomes part of what you are measuring. The same physical world supports both descriptions. This relationship is common in physics. Water can be treated as a continuous fluid when we study waves or plumbing, even though we know it is made from molecules. Air can be treated as a continuous gas in many calculations, even though it contains individual molecules. A solid can be treated as a continuous elastic material when we calculate how a building responds to vibration, even though the building is made from atoms. The fact that one description works at a large scale does not mean the microscopic description is false, and the fact that a microscopic description exists does not make the large scale one useless. Quantum mechanics often sits underneath classical physics in exactly this way. The smooth sounds of everyday life emerge from enormous numbers of quantum interactions. There are so many particles, so many vibrational excitations, and so many exchanges with the surrounding environment that individual quantum steps become practically invisible. What reaches us is a stable classical pattern. This helps explain why the world around you does not seem obviously quantum, even though everything in it obeys quantum physics. Your table does not appear to exist in a delicate superposition whenever you put down a cup. Your headphones do not seem uncertain about whether they are producing music. A door closing produces a definite sound rather than an obvious collection of quantum possibilities. Large systems interact constantly with their environments. They contain huge numbers of particles and large amounts of thermal activity. The quantum details become averaged and dispersed in ways that make classical behavior an excellent description. Quantum acoustics becomes possible by reversing some of those conditions. Researchers make systems small, they cool them, they isolate particular vibrational modes, they reduce thermal noise, they prevent phonons from leaking into unwanted parts of the device. Once enough of the ordinary background activity has been removed, the quantum structure becomes measurable. The important point is that scientists have not changed the rules of sound. They have created conditions where rules that were always present can no longer be ignored. A loudspeaker in your room and a microscopic resonator in a quantum laboratory are both mechanical systems governed ultimately by quantum physics. The difference is that the loudspeaker contains such a large number of excitations and interacts so strongly with its surroundings that treating it classically is far more useful. A carefully cooled resonator containing one excitation is another matter. There, the difference between one phonon and two phonons can become the entire point of the experiment. This also tells us why there is no universal smallest piece of sound in the simple sense we might expect. One phonon is one quantum of a particular vibrational mode, but different modes have different frequencies and therefore different quantum energies. A phonon associated with one vibration does not have the same energy as a phonon associated with another frequency. There is no standard sound atom from which every noise in the universe is assembled. Instead, each vibrational system has modes, and quantum mechanics determines the excitation structure of those modes. This is another reason the word particle needs context. If phonons were ordinary permanent objects, we might expect all of them to carry the same basic properties, regardless of where they existed. But a phonon is defined through the material and mode that supports it. Change the material and the possible vibrations change the structure and the phonons change with it. A phonon in one crystal and a phonon in another may behave very differently, because the underlying materials are different. The material therefore does not merely provide a container through which phonons happen to move. The material creates the very conditions that make those phonons possible. This is one of the central ideas in condensed matter physics. A large collection of particles can organize itself in ways that produce new effective objects. Those objects may have properties that would make no sense for the individual particles considered alone. Phonons are only one example. Materials can support many kinds of quasi-particles and collective excitations. Studying them often tells us more about how the material behaves than staring at the individual atoms would. Sound gives us a particularly intuitive route into this idea because we already understand that a vibration is collective. When a bell rings, we know the entire bell is participating in some complicated motion. We do not expect one particular atom to be responsible for the note. Quantum physics takes that familiar collective behavior and shows us that its energy has a discrete structure. There is another question we should deal with before finishing. If sound is a pattern rather than a material substance, does sound exist before something hears it? Physically, the answer is straightforward. Mechanical vibrations and pressure waves do not require a listener. A falling object can create a disturbance in air whether a person is nearby or not. A crystal can contain phonons without a human observer. A mechanical resonator can vibrate inside a laboratory while everyone has gone home. Hearing is something additional. It is what happens when a sound-related disturbance interacts with an auditory system and the brain processes the result. That distinction matters because ordinary language uses the word sound in two slightly different ways. Sometimes we mean the physical wave. Sometimes we mean the conscious experience produced by hearing it. Physics mainly studies the first. Your experience of a violin note is not contained inside the air molecules. The air carries pressure variations. Your auditory system converts those variations into biological signals, and your brain produces the perception of pitch, loudness, location, and tone. The physical pattern and the experience are connected, but they are not identical. This becomes especially obvious with vibrations outside human hearing. Ultrasound is physically real even though we cannot hear it. Vibrations inside a quantum device are physically real even when their frequencies are completely inaccessible to an ear. Nature does not divide mechanical waves into sound and not sound, according to what humans happen to detect. Our hearing range is simply one small biological window onto a much larger range of vibration. So when we ask what sound is made of according to quantum physics, the answer needs several layers. The material itself is made of quantum particles such as atoms and their constituents. Those particles interact. Their interactions allow collective vibrations. Quantum mechanics assigns discrete excitations to the vibrational modes. Those excitations are phonons. When enormous numbers of those excitations and microscopic motions combine, the result can behave like the smooth classical waves we call sound. If that sounds less satisfying than discovering a tiny object at the bottom of everything, it is because nature does not always organize itself according to the simplest kind of question. Sometimes asking what something is made of works beautifully. A molecule is made from atoms. A nucleus contains protons and neutrons. Other things are better understood by asking what the system is doing. A wave is not mainly a new kind of substance. It is behavior. A vibration is behavior. Sound is behavior. A phonon is the quantum description of a particular unit of that collective behavior. This is why sound connects everyday physics with some of the most important ideas in modern quantum theory. It shows us how classical waves emerge from quantum systems. It shows us how collective motion can be treated using particle-like excitations. It shows us that quasi-particles can be experimentally real without being fundamental particles. It also shows us that the same vibration responsible for something as ordinary as a tone can become part of heat conduction, electrical resistance, superconductivity, precision measurement, and quantum information technology. The next time you hear a familiar sound, none of this will be obvious. A door will simply close. Rain will simply hit the window. Music will simply arrive through a speaker. Someone will speak and you will understand the sentence without thinking about air pressure, atomic motion, or quantized vibrational modes. That is probably for the best. Conversation would become rather slow if everyone stopped after every word to consider the microscopic state of the surrounding medium. But underneath that effortless experience is a remarkable chain of physical events. Matter moves. Neighbouring matter responds. A disturbance propagates. Energy changes form. Microscopic vibrations obey quantum rules. Your ear responds to a tiny part of that motion, and your brain turns the result into something meaningful. We began by asking what sound is made of, and the answer turned out not to be a single object. Sound is a collective mechanical process. At the scale of ordinary life, waves are the useful description. At the quantum scale, phonons give us a way to describe discrete excitations of those vibrations. Neither picture needs to be thrown away. The wave tells us how the disturbance spreads. The phonon tells us how vibrational energy behaves when its quantum structure matters. And perhaps the easiest way to remember the distinction is this. A phonon is not a tiny piece of material that creates sound. It is one quantum of an organized vibration that the material itself is capable of supporting. If you are still awake, take a moment to notice whatever sounds are around you now. Perhaps there is a quiet fan, traffic outside, rain, distant voices, a heating system, or only the small sounds of the room and your own breathing. Every one of them begins with matter moving somewhere. Some of those movements travel through solids before reaching the air. Some may have reflected from several surfaces. Some have already lost part of their energy into microscopic vibrations that will eventually become heat. At the deepest practical level we have explored tonight, all of those ordinary motions belong to matter that follows quantum rules, even when the result looks completely classical. So if someone asks whether sound is made of waves or particles, you do not have to choose one and discard the other. Sound travels as a mechanical wave at the scale we normally experience, while the vibrational modes underneath that wave can have quantum excitations called phonons. The two descriptions belong to different scales of the same physical process, and that brings us back to where we started listening. Wherever you are listening from tonight, the voice reaching you now has been carried by a long sequence of vibrations and conversions. A recording became an electrical signal, a speaker or headphone moved, matter around it responded. Your ear detected the resulting disturbance, and your nervous system did the rest. If you found this journey through sound relaxing or useful, you can like the video and subscribe to Physics with William. It helps more people find these slower explorations of the ordinary things that become much more interesting once we ask how they actually work. For now, there is nothing more you need to measure, detect, or count. The phonons can continue with their microscopic business without supervision, the surrounding air can keep carrying its small pressure changes, and whatever quiet sounds remain around you can simply be part of the room again. Sleep well, and wherever you are listening from, I hope the rest of your night is a quiet one.